In 1987, Nelson Mandela died in prison, or at least that is what millions of people across the world distinctly remember, which is precisely why this phenomenon bears his name. Yet when we examine the historical record, we find that Nelson Mandela was actually released from prison in 1990, went on to become president of South Africa, and lived until 2013. A timeline that contradicts the vivid memories held by countless individuals who swear they attended his funeral decades before his actual death. The term Mandela Effect was coined to describe this peculiar phenomenon, where large groups of people share false memories of events that never occurred or happened differently than remembered. And what makes this truly unsettling is not simply that people misremember things, because human memory is notoriously fallible and prone to distortion, but rather that these false memories are often shared across completely separate populations with no prior communication or influence between them. People around the world report identical misrememberings, such as the Berenstain Bears actually being spelled Berenstain, or the Monopoly mascot Mr. Monopoly never having had a monocle despite countless memories suggesting otherwise, or the famous Star Wars quote being Luke, "I'm your father," rather than "No, I'm your father." And these shared false memories demonstrate something far more troubling about the nature of collective human consciousness and the reliability of our shared reality. The psychological mechanism behind these effects likely involves a combination of factors including source confusion, where the brain conflates similar or related information from different sources, and false memory implantation, where suggestion and social reinforcement can actually create or solidify entirely fictional memories within our minds. When we encounter others describing the same false memory, our brains interpret this social consensus as confirmation, thereby strengthening the neural pathways associated with that false memory until it feels indistinguishable from genuine recollection. What persists despite the clear logical explanations is our profound unease with these instances, because even understanding the psychological mechanisms does not eliminate the eerie sensation that something has fundamentally shifted, that we are somehow observing timeline inconsistencies or glitches in a constructed reality where multiple people from different backgrounds and countries spontaneously develop the identical false memory without any reasonable explanation for why their brains would malfunction in precisely the same way. Perhaps this is why the Mandela Effect continues to captivate us, not because it reveals anything definitively true about reality itself, but because it exposes the unsettling gap between what we believe we know and what actually is, forcing us to confront the possibility that our most confident memories might be elaborate constructions, indistinguishable from truth, yet fundamentally false. Imagine two particles that become so fundamentally connected that they share a single quantum state, regardless of the distance separating them, whether they are separated by millimeters or by the entire width of the observable universe. And when you measure one particle and force it to adopt a definite state, the other particle instantaneously responds by adopting a complementary state. A phenomenon that Einstein himself called spooky action at a distance, because it seemed to violate the basic principle that nothing can travel faster than light. Yet experiments conducted over decades have repeatedly confirmed that this is exactly what happens in the quantum realm, with particles behaving as though they are communicating with each other instantaneously across any conceivable separation. The mechanism underlying this phenomenon stems from the fundamental nature of quantum superposition, where particles do not possess definite properties until they are measured, existing instead in a state of probability and potential. And when two particles become entangled through interaction or creation, their properties become linked in such a way that measuring one immediately determines the properties of the other. Not through any signal passing between them, but through a shared quantum state that encompasses both particles as a unified whole, transcending our classical understanding of separate objects existing in separate locations. What makes this phenomenon profoundly strange is that we have experimentally verified it works, we have built technologies based upon it, we have integrated it into quantum computing and quantum cryptography, and yet we have simultaneously accepted that we do not fully understand the mechanism by which it operates. We have normalized the existence of phenomena that suggests reality operates according to rules fundamentally different from the intuitive mechanical universe we perceive in everyday life. And we continue operating within this contradiction without demanding a complete answer, allowing quantum entanglement to persist as an established scientific fact that nonetheless challenges our deepest assumptions about causality, locality, and the structure of space and time itself. Perhaps the most humbling aspect of quantum entanglement is that it forces us to confront the limits of human intuition itself, that our evolved brains, shaped to navigate a macroscopic world of separate objects and local causes, may be fundamentally ill-equipped to grasp the deepest nature of reality, and that accepting this limitation might be the truest form of scientific wisdom. This surrender to mystery is not a failure of science, but rather its greatest strength, the ability to map the boundaries of human knowledge and continue exploring beyond them, suggesting that the universe's deepest secrets may require us to develop entirely new ways of thinking, new languages, and new frameworks for understanding that transcend the limitations of classical logic itself. In this light, quantum entanglement serves as a humbling reminder that the universe is not obligated to make sense to us, and that our willingness to sit with paradox and uncertainty may be precisely what allows us to glimpse truths that a more rigid mind could never perceive. The greatest discoveries often emerge not when we demand answers, but when we become patient enough to live within the questions themselves. Imagine a wall with two small openings cut into it, positioned side by side, and behind this wall sits a screen designed to detect particles fired toward it. And when scientists send electrons or photons toward these two slits, something profoundly unsettling occurs that challenges the very foundation of how we understand reality itself. When no one is watching, when no measurement apparatus is present to determine which slit the particle passes through, the particles behave as waves, passing through both slits simultaneously and creating an interference pattern on the detection screen, a pattern that reveals the particle existed in multiple states at once, occupying both possible paths as though probability itself were physically real. However, the moment scientists set up equipment to observe which specific slit each particle actually goes through, the behavior changes instantaneously, and the particles stop acting like waves and start acting like ordinary particles, passing through only one slit or the other, and the interference pattern vanishes entirely, replaced by two distinct bands of impact. The mechanism underlying this phenomenon appears to be consciousness or measurement itself, suggesting that the act of observation fundamentally alters quantum reality at the smallest scales, that particles somehow know they are being watched and respond by changing their behavior, collapsing from a state of infinite possibility into a single definite state. This creates a logical paradox because if particles behave differently when observed versus unobserved, then reality itself seems to be dependent on the presence of observers, implying that nothing possesses definite properties until someone or something measures it. And yet we continue to operate under the assumption that an objective world exists independently of our perception. We have normalized this strangeness by confining it to the quantum realm, treating it as something that only applies to impossibly small scales, and assuming the macroscopic world operates by different rules. But no one has ever successfully explained where the boundary between quantum and classical physics actually lies, or why the rules should change at all. Perhaps the most disturbing possibility is that there is no boundary at all, that observation and consciousness play a role at every scale of reality, and we simply lack the sensitivity to detect it in the everyday world, meaning that the universe we experience as solid and objective may be far more participatory and observer-dependent than our intuition allows us to accept. If this is true, then every act of perception, every glance, every measurement, every moment of attention becomes a subtle act of creation, and the distinction between observer and observed dissolves into something far more intimate and unsettling than science has traditionally been willing to acknowledge. And yet, despite decades of experimental refinement and philosophical debate, we remain unable to definitively answer the most fundamental question. Does the universe require consciousness to exist, or does consciousness merely reveal what was always there, hidden beneath layers of probability and potential? This uncertainty sits at the heart of physics like an unsolved koan, demanding that we either expand our understanding of reality itself or admit that some mysteries may lie permanently beyond the reach of empirical science. At the quantum level, something genuinely strange occurs whenever scientists attempt to measure the behavior of subatomic particles, a phenomenon that has puzzled physicists for nearly a century and continues to challenge our fundamental understanding of reality itself. When researchers set up experiments to detect whether an electron travels through one slit or another in the famous double-slit experiment, the very act of observation fundamentally changes the outcome, causing the electron to behave as a particle rather than as a wave, a shift that occurs instantaneously the moment measurement begins. Yet when no observation takes place, when no detector is positioned to catch the electron in the act, it behaves as a wave, passing through multiple paths simultaneously in a superposition that defies classical logic, suggesting that the universe itself operates differently depending on whether anyone is watching. The mechanism underlying this phenomenon stems from the fact that all measurement requires interaction, that to observe a particle you must bombard it with photons or other particles, and this bombardment itself physically alters the system being measured, collapsing the quantum wave function into a definite state. It is not consciousness itself that causes this change, not some mystical human awareness bending reality to our will, but rather the unavoidable physical interaction required by the measurement apparatus, a distinction that somehow becomes lost in popular understanding and in the folklore that surrounds quantum mechanics. What remains profoundly unsettling is that we have accepted this phenomenon as simply how nature works at its deepest level, that we have incorporated the idea that observation and reality are inseparable into our scientific worldview without fully grappling with the philosophical implications of a universe that apparently cannot exist in a definite state without being observed. Without acknowledging how bizarre and counterintuitive this truly is compared to the mechanical universe we experience in our everyday lives. Perhaps the most unsettling aspect is that this principle extends beyond electrons and photons to larger systems, suggesting that reality at every scale may be fundamentally participatory, that the universe does not possess definite properties independent of measurement, and that we are not merely passive observers of nature but unavoidable participants in its actualization. This participatory universe raises an unavoidable question. If reality requires observation to crystallize into definite form, what was the state of the cosmos before conscious observers evolved to perceive it? And does this imply that the universe itself somehow brought consciousness into being as a necessary precondition for its own existence? These questions push us toward interpretations like the participatory Anthropic Principle, which suggests that observers are not incidental to the universe but essential to it. Yet they remain deeply controversial because they seem to dissolve the boundary between physics and philosophy, between what we can measure and what we can only contemplate. At the heart of quantum mechanics lies one of the most unsettling experiments ever conducted, one that suggests the universe does not actually decide what it is until we observe it, and more disturbingly, that our observations made in the present can retroactively determine what happened in the past. This is the delayed choice experiment, first theorized by physicist John Wheeler in 1983, and subsequently performed in laboratories around the world with results that continue to perplex even those who work with quantum systems daily. The experiment works like this. A photon or electron is sent toward a half-silvered mirror, a device that can either split the particle into two possible paths or allow it to pass straight through. And the crucial element is that the choice of which configuration to use is made after the particle has already been committed to its journey, sometimes milliseconds later, sometimes much later depending on the setup. What the experiment consistently reveals is that the particle behaves as though it somehow knew in advance what choice the experimenter would make, adjusting its behavior retroactively to match the future measurement configuration, collapsing from a state of quantum superposition into a definite outcome only when observed, even though that observation technically came after the moment it should have already been forced into one particular state. The mechanism underlying this phenomenon appears to involve the fundamental nature of reality at quantum scales, where particles exist in all possible states simultaneously until a measurement forces them to choose one. But the truly bizarre aspect is that measurements performed in the present seem to reach backward through time and alter what was real in the past, suggesting that reality itself is not written until the moment we look at it. Scientists have proposed various interpretations to explain this without admitting that causality can flow backward. The Copenhagen interpretation suggests we simply cannot talk about what the particle was doing before measurement. The many worlds interpretation claims all possibilities actually happen in branching universes, and other frameworks attempt to preserve some sense of objective reality. Yet despite decades of refinement, despite the experiment being repeated in increasingly sophisticated ways, despite our best theoretical frameworks being stretched to accommodate these findings, we continue functioning in a world where we treat the past as fixed and settled, where we assume objects have definite properties whether we are looking at them or not, where we rely on causality flowing only forward through time. The delayed choice experiment reveals a fundamental crack in our understanding of existence itself, a suggestion that observation and reality are not separate things, but are somehow woven together in a way that defies our intuitive sense of how the universe should work. Yet this bizarre truth remains confined largely to the world of physics papers and quantum laboratories rather than reshaping how we understand consciousness, time, and the nature of existence itself in any meaningful way that would ripple through our culture and philosophy. In 1984, a physicist named John Wheeler proposed a thought experiment that would fundamentally challenge our understanding of observation and reality itself. And decades later, scientists actually built the experiment and watched it work exactly as Wheeler predicted, which means that the past can be retroactively changed by decisions made in the present. A concept so disturbing that most people have never even heard of it, despite the fact that it has been verified countless times in laboratories around the world. The quantum eraser experiment works like this. You fire individual photons at a barrier with two slits, and normally when no one is watching which slit the photon goes through, it behaves like a wave and creates an interference pattern on the detector screen behind the barrier. But the moment you set up a detector to observe which slit the photon actually passes through, the photon immediately behaves like a particle and the interference pattern disappears, which is strange enough, but here is where it becomes genuinely unsettling. If you then erase the information about which slit the photon went through after it has already passed through the barrier, the interference pattern comes back, meaning that the photon retroactively changes its behavior based on information that is erased in the future, information that cannot possibly have affected its past journey. What this reveals is that observation itself is not a passive act of looking at reality, but rather an active process that fundamentally shapes which version of reality actually manifests. And furthermore, this shaping can occur backwards through time, suggesting that the universe does not have a predetermined past, but rather a past that crystallizes only when observed or measured. The mechanism behind this phenomenon appears to involve the quantum state existing in a kind of superposition of all possibilities, until the moment of measurement forces it to collapse into one definite outcome. And if you then remove the information that would have forced that collapse, the quantum system reverts to its superposition state and explores all possibilities again. But we have become so accustomed to treating this as merely a technical quirk of quantum mechanics that we rarely stop to consider what it means. That reality itself appears to be fundamentally participatory, that nothing becomes real until something observes it, and that the past is not fixed, but rather continuously rewritten by present choices and future measurements, which should by all rational standards seem impossible, and yet remains consistently reproducible and is now considered established science. Buried quietly in physics textbooks while the world continues operating as though the past is solid and observation is passive, and reality exists independent of whether anyone is watching. Yet when you consider that human consciousness itself may be fundamentally entangled with the quantum processes underlying reality, the implications become even more vertiginous. Perhaps the act of you reading these words, of your mind processing this information, subtly reshapes not just the future but the very past that led to this moment, collapsing infinite possibility chains into the singular thread of history you now experience. Imagine a physicist named Wigner who is waiting outside a laboratory while his friend conducts a quantum measurement experiment inside. Before the friend opens the lab door to report the results, Wigner must consider what has actually happened to the quantum system, and here emerges one of the most disorienting paradoxes in modern physics. According to the standard interpretation of quantum mechanics, a quantum system exists in a superposition of all possible states until someone observes it, at which point the wave function collapses and reality crystallizes into a single outcome. But the question becomes devastatingly circular: who counts as the observer? When Wigner's friend measures a quantum particle inside the lab, does the wave function collapse at that moment, or does it only collapse when Wigner learns about the measurement by opening the door and observing his friend? The paradox deepens when we consider that from Wigner's perspective outside the lab, both his friend and the entire experimental apparatus remain in a superposition of all possible measurement outcomes until he gains information about them. Yet from the friend's perspective inside the lab, the measurement has absolutely occurred and the wave function has already collapsed. These two descriptions of reality cannot both be true simultaneously, and yet both follow logically from the standard quantum mechanical framework. What makes this genuinely strange is that there is no objective fact of the matter about when or whether the measurement actually happened. The very concept of an independent, observer-independent reality seems to dissolve under scrutiny. Physics textbooks teach this paradox as a curiosity, a philosophical puzzle worth pondering, but not something that fundamentally breaks our understanding of how the universe operates. Yet for decades, physicists have continued working with equations that cannot assign an objective description of reality to a simple laboratory scenario. We have normalized a foundational inconsistency, treating it as an interpretive ambiguity rather than evidence that something is profoundly wrong with how we understand the relationship between consciousness, measurement, and physical reality itself. The paradox becomes even more acute when we imagine chains of observers. Wigner's friend could have an assistant, who has a colleague, each nested within their own classical reality while existing in superposition from an external perspective. This infinite regress suggests that either consciousness plays a fundamental role in collapsing wave functions, or the entire framework of quantum mechanics requires radical reconceptualization to accommodate multiple simultaneous valid descriptions of the same physical event. Some physicists have proposed that quantum mechanics might permit genuinely incompatible descriptions of reality, that Wigner and his friend are both correct within their respective domains, forcing us to abandon the classical assumption that a single objective reality exists independent of perspective. Others suggest the paradox reveals that consciousness itself may be a fundamental feature of physics, not merely an observer of it, though this path leads into speculative territory where empirical testing becomes nearly impossible. In 1935, a physicist named Erwin Schrödinger proposed a thought experiment that would become one of the most misunderstood and paradoxical illustrations of quantum mechanics ever conceived. And it began with a simple yet deeply unsettling question about what happens when we place a cat inside a sealed box alongside a radioactive atom, a Geiger counter, and a mechanism designed to release poison gas if and only if the atom decays. The setup is elegantly cruel in its simplicity. We close the box and cannot observe what is happening inside, and according to the rules of quantum mechanics, that radioactive atom exists in what physicists call a superposition, meaning it is both decayed and not decayed simultaneously until the moment we open the box and measure it. This creates an immediate logical catastrophe because if the atom is truly in both states at once, then the poison gas is both released and not released, which means the cat inside is both dead and alive at the same time, existing in some ghostly hybrid state that defies every instinct we possess about how reality should function. Schrödinger himself actually invented this thought experiment not to celebrate quantum mechanics, but to demonstrate how absurd it would be to apply quantum rules to the macroscopic world, and yet the image has become so iconic that it has transcended his original intent and now represents something far stranger in our collective consciousness. The psychological mechanism at work here is that the thought experiment perfectly crystallizes our deepest discomfort with quantum uncertainty. The idea that reality itself is fundamentally ambiguous, that observation creates reality rather than merely revealing it, and that there exists a range of scales at which the universe operates according to principles that feel almost magical rather than mechanical. We have normalized this broken aspect of reality by treating it as an established fact rather than an ongoing philosophical crisis, teaching it in universities as settled science, while simultaneously acknowledging that nobody really understands what it means. And this peculiar acceptance of mystification disguised as knowledge persists because quantum mechanics works perfectly well for making predictions and building technology. Even though the underlying interpretation of what is actually happening remains contested and genuinely mysterious, allowing us to maintain both scientific confidence and fundamental confusion in the same moment. The cat has become our mascot for this productive uncertainty, appearing on t-shirts and coffee mugs as a kind of intellectual badge of honor, while the actual philosophical problem it represents, whether quantum superposition applies to macroscopic objects, whether consciousness plays a role in collapse, whether multiple worlds branch at every measurement, remains fundamentally unresolved, a reminder that our most powerful scientific tool is also our most honest admission of ignorance. And perhaps this is precisely why the cat refuses to leave us. It serves as a humble monument to the boundary of human understanding, a furry reminder that even our greatest intellectual achievements rest upon foundations we have not yet fully examined, and that sometimes the most profound scientific insights are those that force us to admit, with genuine humility, that reality is far stranger and more subtle than our intuitions could ever prepare us for. Imagine a particle trapped behind a barrier so high that, according to classical physics, it should never escape, and yet it does. Quantum tunneling represents one of the most profoundly counterintuitive phenomena in modern physics, where subatomic particles pass through solid barriers as though those barriers do not exist, emerging on the other side without ever having possessed enough energy to climb over them in the first place. This is not a theoretical curiosity confined to abstract mathematics or isolated laboratory experiments. Quantum tunneling occurs constantly throughout the universe and within the very cells of your body. It is responsible for the nuclear fusion reactions that power the sun itself, allowing protons to fuse despite the enormous electromagnetic repulsion that should keep them eternally apart. In semiconductors and transistors, the electronic devices that comprise every computer and smartphone in existence, tunneling events occur billions of times per second, making modern technology functionally dependent on a phenomenon that appears to violate everything we understand about how physical barriers work. The mechanism underlying this reality-bending behavior stems from the fundamental nature of quantum mechanics and the probabilistic wave function that describes particle behavior. At the quantum scale, particles do not possess definite locations or velocities, but rather exist as probability distributions, as clouds of possibility spread across space. This wave function does not abruptly end at the barrier boundary, but rather extends through and beyond it, decaying exponentially but never quite reaching zero. There exists a non-zero probability, however small, that the particle's position is on the opposite side of the barrier, and this probability manifests as a real, measurable phenomenon with observable consequences. The particle does not tunnel through the barrier in any literal sense that aligns with our macroscopic intuition. Rather, it simply appears on the other side through a legitimate reading of quantum mechanics itself. What renders this particularly strange is not merely that it happens, but that we have become so accustomed to it existing that we scarcely pause to marvel at its fundamental wrongness. Engineers calculate tunneling probabilities and design devices around it as casually as architects design buildings around gravity, treating it as a known variable rather than an active assault on causal logic. Yet this normalization of the impossible reveals something profound about scientific progress. What once seemed to violate the laws of physics becomes, through understanding, merely an overlooked clause in nature's actual rulebook, a reminder that reality operates according to principles far stranger and more permissive than our everyday experience suggests. Perhaps this is the deepest lesson quantum tunneling offers, that the universe is not constrained by our intuitions about solidity and barriers, but rather operates through layers of probability and possibility that reward those willing to look beyond the apparent impossibility of things. In this sense, the particle that tunnels through the barrier is not defying nature. It is simply taking a path that nature, all along, had always permitted. In the vast mathematical landscape of thermodynamics and cosmology, there exists a deeply unsettling hypothesis that strikes at the very foundation of how we understand consciousness and existence itself, a concept known as Boltzmann Brains, which posits that in an infinitely old universe with infinite matter and energy, random quantum fluctuations become statistically inevitable across incomprehensibly large scales of time, and given enough time, far longer than the current age of our universe. The laws of physics dictate that a conscious brain could spontaneously assemble itself from nothing, fully formed with false memories of a past that never occurred, experiencing what it believes to be a coherent reality that is entirely illusory and constructed only within that singular moment of its existence before entropy reclaims it. The mechanism underlying this disturbing possibility stems from Ludwig Boltzmann's work in statistical mechanics, which demonstrates that any sufficiently complex system can theoretically emerge through pure random chance, no matter how improbably, and when applied to the entire cosmos across infinite timespan, even events with odds so minuscule that they defy rational comprehension become not merely possible, but virtually certain to occur somewhere, somewhen. Which means that stray atoms drifting through the void could randomly collide and arrange themselves into neural tissue, complete with synaptic connections firing in patterns that generate consciousness, all by accident and without any evolutionary process or physical causation behind it. What renders this concept particularly troubling is not merely its logical coherence within our current mathematical frameworks, but rather that observers like ourselves cannot easily distinguish whether we are part of a genuinely evolved biosphere with actual history, or whether we ourselves might be Boltzmann brains that spontaneously fluctuated into conscious existence mere moments ago with implanted false memories of childhoods and relationships, and entire lifetimes that never truly happened, since the subjective experience would be indistinguishable from authentic reality. Yet this problem persists in serious cosmological and philosophical discourse precisely because our best models of the universe do not provide an easy mechanism to exclude it, leaving us suspended in a state where reality's basic intelligibility remains fundamentally uncertain, and we continue our daily lives in full knowledge that our entire existence might be nothing more than a statistical accident in an infinite void with no causal history whatsoever. Yet perhaps most paradoxically, the very fact that we can contemplate this possibility, that consciousness itself can recognize its own potential illusory nature, suggests a kind of recursive awareness that even a randomly assembled brain would possess, implying that truth and illusion become philosophically indistinguishable when filtered through the lens of subjective experience alone. This paradox ultimately transforms Boltzmann brains from a mere cosmological curiosity into a profound epistemological mirror, forcing us to confront whether the scientific method itself, our most reliable tool for understanding reality, can ever truly validate its own foundations, or whether we are forever condemned to build our towers of knowledge upon ground that might dissolve into statistical noise at any moment. Consider the possibility that we are living inside a computer simulation, a concept that has moved from the margins of philosophy into serious consideration by physicists, technologists, and academics worldwide, and this shift itself reveals something peculiar about how we perceive reality. The simulation hypothesis proposes that the universe we experience, with all its laws of physics, the stars above us, the ground beneath our feet, and the very consciousness we use to observe it all, might be nothing more than an elaborate digital construct created by a vastly more advanced civilization existing in a higher layer of reality. What makes this hypothesis particularly unsettling is not merely its theoretical possibility, but the logical chain of reasoning that supports it, beginning with the observation that technology advances exponentially, and that civilizations capable of creating simulated universes would likely create many of them, statistically suggesting that any random consciousness would be far more likely to exist within a simulation than in the original base reality. The hypothesis gains additional credibility from the peculiar discoveries of quantum mechanics, which reveal that particles behave differently when observed than when unobserved, that reality at the subatomic level appears to lack definite properties until measurement occurs, and that the universe seems fundamentally probabilistic rather than deterministic in ways that mirror the operational constraints of a computer program rather than the behavior of classical physics. Furthermore, the existence of mysterious constants in physics, the mathematical precision underlying natural laws, and the Anthropic Principle suggesting that the universe is calibrated with remarkable specificity to allow conscious observers to exist, all lend an eerie plausibility to the simulation interpretation. Yet despite these logical threads that weave together into a compelling argument, most people continue navigating their daily lives with absolute certainty in the fundamental reality of their experience, dismissing the simulation hypothesis as mere science fiction or philosophical curiosity, even as physicists publish peer-reviewed papers exploring its validity and technologists acknowledge the eventual capability to create such simulations. We have normalized the dismissal of this possibility through cultural consensus and the sheer psychological difficulty of truly accepting that everything we experience might be fundamentally unreal, choosing instead the comfortable assumption that our reality is base reality, that our consciousness is properly grounded in authentic existence, without ever genuinely interrogating whether this assumption rests on anything more substantial than habit and social agreement. Yet this very dismissal may itself be the most telling evidence. If we were simulated entities, our creators might deliberately engineer our psychology to resist this conclusion, instilling us with an almost unshakable intuition that our reality is fundamental, rendering the simulation hypothesis unfalsifiable not because it lacks merit, but because our cognitive architecture may be specifically calibrated to reject it. Consider the profound strangeness of mathematics itself. We have invented a system of abstract symbols and logical rules that somehow, inexplicably, describes the physical world with stunning accuracy. Physicists and mathematicians have long observed that the universe appears to operate according to mathematical principles, as though reality itself were written in the language of equations and geometric forms. Eugene Wigner famously called this the unreasonable effectiveness of mathematics in the natural sciences, a phrase that captures the bewildering fact that abstract human constructs seem to mirror the deepest patterns of nature. When we derive a mathematical formula through pure logical reasoning, we later observe that phenomenon occurring in the real world with precision. Electrons behave as the equations predict, galaxies move according to gravitational mathematics, quantum fields collapse into measured values that match our theoretical predictions. Yet here lies the conceptual vertigo. We cannot explain why this should be the case at all. Mathematics is a human creation born from our minds, shaped by our cognitive limitations and cultural traditions. The symbols we use are arbitrary. The axioms we choose are choices we made. Yet somehow these invented abstractions correspond to objective reality in ways that seem far too perfect to be coincidental. The psychological mechanism at work here involves our tendency to assume that understanding requires explanation, that if mathematics works, there must be a deeper reason. But the reason might not exist. Reality might simply be mathematical in nature, meaning there is no further explanation to find. Or mathematics might describe reality only because we designed it specifically to do so, creating a circular truth that we then mistook for a discovery. The second mechanism involves how we have normalized this uncanny correspondence. We teach mathematics in schools as if it were a transparent language for describing nature, rather than treating it as one of humanity's most bewildering mysteries. Students learn equations without questioning the fundamental strangeness of why abstract symbols and logical operations should correspond to actual physical events. This normalization allows us to ignore the unsettling possibility that either our understanding of reality is fundamentally incomplete, or that the distinction between abstract mathematics and physical reality might itself be illusory. Perhaps the universe is not described by mathematics. Perhaps it actually is mathematics. This possibility persists in the background of scientific thinking without ever becoming a crisis, because we have collectively decided that mathematical accuracy is sufficient justification for not asking why mathematics works at all. We accept the map as equivalent to the territory, and in doing so, we may have stopped wondering whether the map and territory were ever truly separate things at all. The mathematical universe hypothesis, that physical reality is literally a mathematical structure, shifts this from unsettling mystery to potential truth, but only by transforming the question of why into the deeper question of what does it mean for anything to exist outside of mathematical form. Imagine a universe where everything you see, touch, and experience exists as a projection on a distant two-dimensional surface, much like a hologram created from a laser and a photographic plate, and that your three-dimensional reality is merely an elaborate illusion generated from information encoded on a boundary far beyond the reach of human perception or measurement. This is the holographic principle, a stunning theoretical framework emerging from string theory and quantum gravity that suggests the entire cosmos, with all its galaxies, stars, planets, and conscious observers, could be completely described by information existing on a lower dimensional boundary, a mathematical surface that contains all the data necessary to reconstruct our apparent three-dimensional world. The principle originated in the 1990s when physicist Juan Maldacena discovered a remarkable mathematical correspondence between a gravitational theory in a higher dimensional space and a quantum field theory on its lower dimensional boundary, suggesting that what we perceive as depth and volume might be redundant information, that the true complexity of reality resides on a simpler, flatter substrate. The psychological weight of this concept derives from a fundamental cognitive dissonance between the intuitive solidity of our experience and the radical suggestion that this solidity is derivative, that we are not inhabitants of a fundamentally three-dimensional universe, but rather observers of a projection, much as characters in a video game might be unaware that their world is rendered on a two-dimensional screen. We navigate our lives with the absolute certainty that depth and space are foundational properties of existence, Yet modern physics proposes that these very qualities might be emergent phenomena, secondary consequences of information processing occurring elsewhere, at the edges of spacetime itself. What renders this principle particularly destabilizing is that it remains mathematically consistent with our most rigorous observations of quantum mechanics and gravity, suggesting that our deepest equations are pointing toward a conclusion that contradicts our most basic assumptions about the nature of reality. Yet we continue building our technologies, our civilizations, and our understanding on the premise that three-dimensional space is genuine and primary rather than provisional and projected. And yet, if the holographic principle is correct, the very act of you reading these words, the neural firing patterns in your brain, the consciousness that seems to arise from three-dimensional biological processes, would itself be a projection of information encoded on some distant cosmic boundary, making the observer and the observed equally illusory, equally derived from the same fundamental source of mathematical data. This realization invites a profound humility. If consciousness itself is a holographic projection, then the boundary between observer and observed collapses entirely, and the universe becomes not a stage upon which we act, but a mirror in which the cosmos observes itself through infinite recursive reflections of the same fundamental information. When Stephen Hawking discovered in 1974 that black holes are not entirely black, but emit radiation due to quantum effects near their event horizons, he inadvertently created one of the most profound paradoxes in theoretical physics, a contradiction so fundamental that it challenges the very foundation of how we understand information and the universe itself. The paradox is deceptively simple to state but monumentally difficult to resolve. As a black hole evaporates through Hawking radiation, all the information about the matter that fell into it appears to be irreversibly destroyed, vanishing from the universe in a way that violates one of quantum mechanics' most sacred principles, the principle of unitarity, which demands that information can never truly be annihilated but only transformed and redistributed. This creates a logical catastrophe because if information can be destroyed by black holes, then the deterministic foundation of quantum mechanics crumbles, and the universe becomes fundamentally unpredictable at its deepest level, unable to reverse any process or recover what has been lost. For decades, physicists have grappled with this information paradox, proposing increasingly exotic solutions such as the black hole complementarity principle, which suggests information is both inside and outside the event horizon simultaneously from different reference frames, or the holographic principle, which proposes that all information in the universe is encoded on a two-dimensional surface rather than existing in three-dimensional space as we perceive it. Yet despite these theoretical frameworks and the intellectual effort of the world's greatest minds, no universally accepted resolution has emerged, and the paradox persists in a kind of conceptual limbo where it is neither fully solved nor definitively proven to be unsolvable. What is particularly strange about how science has normalized this paradox is that we have become comfortable living with a fundamental contradiction at the intersection of quantum mechanics and general relativity, accepting it almost as a feature of modern physics rather than a flaw-demanding resolution, as though the universe itself is permitted to be logically inconsistent in ways that would be utterly unacceptable in any other domain of human knowledge or inquiry. Perhaps this acceptance reflects a deeper truth, that our current theories are incomplete scaffolding built over an abyss we do not yet understand, and that the resolution of the information paradox may ultimately require us to fundamentally reimagine not just black holes, but the very nature of space, time, and what it means for information to exist at all. The quantum extremists whisper that perhaps information is not lost, but transformed into subtle correlations in the Hawking radiation itself, patterns too delicate for our current instruments to detect, waiting for a future civilization with godlike measurement capabilities to reconstruct what was devoured. Others suggest that the very question assumes a false premise, that information, as we define it, may be a parochial concept bound to our particular slice of reality, as limited as asking what color the number 7 is. What remains certain is that black holes continue to evaporate in the depths of space, indifferent to our theoretical struggles, each one a small laboratory conducting an experiment we are only beginning to comprehend. Imagine a black hole, that most extreme and final destination in the universe, a region of spacetime so densely packed that not even light can escape its gravitational pull, and yet according to Stephen Hawking's groundbreaking 1974 discovery, These supposedly impenetrable cosmic prisons are not entirely black at all, but rather emit radiation and slowly evaporate over time. This phenomenon, now called Hawking radiation, emerges from one of the strangest intersections in modern physics, where quantum mechanics collides with general relativity at the event horizon itself, the boundary between the observable universe and the infinite darkness beyond. At this boundary, Hawking proposed that quantum fluctuations create pairs of virtual particles constantly blinking in and out of existence, and occasionally one particle falls into the black hole while its partner escapes as real radiation, causing the black hole to lose energy and gradually shrink until it eventually explodes in a final burst. The mechanism behind this phenomenon lies in the profound weirdness of quantum field theory combined with the nature of gravity itself. For near the event horizon, the curvature of spacetime becomes so extreme that it warps the very fabric of quantum fluctuations, separating virtual particle pairs before they can annihilate each other and converting them into genuine observable particles that carry away the black hole's mass. What makes this truly unsettling is that it violates our deepest intuitions about how black holes should behave, for these objects have long been understood as cosmic sinks from which nothing returns. Yet here is mathematics proving that they leak energy and cannot persist forever, that even the most powerful gravitational forces in the universe are subject to quantum corruption and thermodynamic degradation. We have integrated this discovery into our understanding of black holes and modern astrophysics, treating it as an accepted peculiarity of nature rather than a sign that our foundational theories might be fundamentally incomplete. And in doing so, we have normalized the idea that the universe operates according to principles that seem to contradict themselves at the deepest levels. Yet perhaps this contradiction is itself a clue pointing toward a deeper unified theory we have not yet discovered, one that would reconcile quantum mechanics and gravity into a coherent framework where black hole evaporation is no longer paradoxical, but instead a natural consequence of how reality fundamentally operates at the smallest and largest scales simultaneously. Until that day comes, Hawking radiation remains a tantalizing glimpse into the deep structure of reality, a window through which we can observe the universe whispering secrets about the nature of time, information, and what happens to the contents of a black hole when it finally disappears, questions that may ultimately reshape how we understand existence itself. The black hole information paradox, whether the quantum information encoded in matter that falls into a black hole is truly lost forever or somehow preserved in the radiation itself, remains one of the most profound unsolved problems in theoretical physics, suggesting that our current theories, for all their explanatory power, may still be incomplete in ways we are only beginning to comprehend. Imagine the fundamental fabric of reality itself is unstable, sitting precariously on the edge of annihilation, and that at any moment without warning or cause, the universe could simply cease to exist in the most catastrophic way imaginable. This is the concept of vacuum decay, a theoretical physics phenomenon that represents perhaps the most existentially troubling possibility that serious scientists have considered. According to quantum field theory, what we perceive as empty space is not actually empty at all, but rather filled with quantum fields that exist in what physicists call a vacuum state, a baseline energy level that determines the properties and behaviors of all matter and forces in our universe. The problem emerges when physicists realize that this vacuum state may not be the lowest possible energy state, much like a ball resting on a hilltop that could theoretically roll down to an even lower valley if it gained sufficient energy or encountered the right conditions. If the universe's vacuum state is what mathematicians call a false vacuum rather than a true vacuum, then somewhere, somehow, it could spontaneously tunnel into a lower energy state through quantum tunneling, and when this happens, a bubble of the true vacuum would begin expanding outward at the speed of light, obliterating everything in its path and fundamentally rewriting the rules of physics itself as it spreads across the cosmos. The mechanism driving this catastrophic possibility lies in the nature of quantum uncertainty and the probabilistic foundation of reality at the smallest scales, where particles and fields do not behave according to classical deterministic rules, but instead exist in superposition, with probabilities governing their actual manifestation. When applied to the fabric of spacetime itself, these quantum principles suggest that even the ground state of existence operates under similar probabilistic laws, meaning that anywhere in the observable universe, the vacuum could theoretically transition to a lower energy state completely randomly and spontaneously. What makes vacuum decay such a troubling concept is that we have absolutely no way to predict when or if it will occur, no way to prevent it if it does, and no way to observe it coming until it arrives at our location traveling at light speed, ensuring our complete and utter annihilation before we could even register its presence. Yet despite this genuinely apocalyptic theoretical possibility being supported by legitimate quantum field theory mathematics and discussed seriously by physicists at major institutions, humanity continues about its daily existence largely unconcerned, and civilization proceeds with long-term planning, infrastructure investment, and generational thinking as though the universe is guaranteed to remain stable indefinitely, revealing a remarkable capacity for either rational faith in probability or deliberate psychological denial of metaphysical threats that remain entirely beyond our control or comprehension. Imagine that the universe we inhabit, with all its galaxies, stars, planets, and the very laws of physics that govern our existence, is not actually in its lowest possible energy state, but rather sitting precariously in a kind of cosmic bubble, a false vacuum, waiting for the slightest quantum fluctuation to trigger its complete and instantaneous collapse. This is the false vacuum theory, one of the most unsettling concepts in theoretical physics, which suggests that at any moment without warning or precedent, a region of space could spontaneously transition to a lower energy state, and when this happens, the transformation would spread outward at the speed of light, erasing everything in its path and replacing all the fundamental constants and forces of nature with entirely different ones. The mechanism behind this phenomenon lies in quantum field theory, where particles and forces are understood as ripples in underlying quantum fields that permeate all of space, and these fields have energy landscapes with multiple potential minima, much like a ball resting in a valley that is not actually the deepest valley available, suggesting that a more stable configuration exists elsewhere in the energy landscape. When physicists calculated the properties of the Higgs boson discovered at CERN in 2012, they noticed something profoundly disturbing in the numbers. The relationship between the mass of the Higgs particle and other fundamental constants seemed to place our universe right on the boundary between stability and instability, suggesting we might indeed be in a false vacuum, balanced on a cosmic knife edge. What makes this theory particularly unsettling is that it cannot be disproven by observation because we would have no warning and no escape. The bubble of destruction would simply appear somewhere in the cosmos and expand outward, reaching Earth in an instant without any indication of its approach or any possibility of detection beforehand. Yet despite this terrifying implication hanging over theoretical physics like an invisible sword of Damocles, physicists continue their research unfazed, publishing papers and calculations about the probability of vacuum decay as if contemplating the sudden annihilation of all existence is simply another Tuesday at the laboratory, a reflection of how thoroughly we have normalized the idea that reality itself might be fundamentally unstable and temporary. Some physicists have even speculated that the universe we observe might itself be the result of vacuum decay in a previous cosmos, a nested catastrophe stretching backward through time, while others calculate that if decay were to occur, the new laws of physics in the expanding bubble might paradoxically allow for the emergence of entirely new universes, suggesting that even annihilation could be generative. This cyclical vision of cosmic creation and destruction, universes birthing new universes through their own annihilation, transforms the false vacuum from a mere threat into a fundamental feature of reality's architecture, suggesting that instability and transformation might be not bugs in the cosmic program but essential features that enable the perpetual renewal of existence itself. In 2021, physicists at Google announced they had created something that should not exist according to classical physics: a time crystal, a structure that breaks time symmetry in the same way that ordinary crystals break spatial symmetry, and this discovery fundamentally challenged our understanding of what is possible within the laws of thermodynamics and quantum mechanics. A time crystal is a physical system that repeats itself in time without requiring any additional energy input, meaning it maintains a periodic pattern that evolves indefinitely without ever reaching thermal equilibrium, which violates what we thought we knew about entropy and the arrow of time itself. The researchers created this state using quantum processors by manipulating qubits in a specific configuration that caused them to oscillate in a repeating temporal pattern. and they observed that this pattern persisted for longer than should be theoretically possible according to conventional understanding of quantum decoherence and energy dissipation. The mechanism behind time crystals involves quantum entanglement and the creation of a non-equilibrium state that somehow resists the universe's relentless push toward disorder and homogeneity, and researchers believe that time crystals could eventually be used in quantum computing and extremely precise timekeeping devices, though the practical applications remain largely theoretical at this stage. What makes this discovery particularly unsettling is how casually the scientific community has integrated it into our conception of reality, with multiple research teams now successfully creating and studying time crystals. And yet this fact barely penetrates public consciousness despite representing a genuine crack in our fundamental understanding of how time itself operates. We have normalized the existence of structures that rotate through time rather than space, that oscillate eternally without losing energy, that break symmetries we assumed were inviolable, and we continue with our daily lives as though the discovery that time might have crystalline structures comparable to salt or diamonds is merely another interesting paper in a peer-reviewed journal rather than a profound revelation about the nature of reality itself. Perhaps this is because time crystals, like so many genuine mysteries of physics, inhabit a strange liminal space where they are simultaneously real and incomprehensible. We can measure them, replicate them, write equations describing them, and yet they remain fundamentally alien to human intuition, existing in quantum regimes so removed from our everyday experience that they inspire neither the visceral wonder of black holes nor the practical urgency of climate change. Perhaps the greatest irony is that time crystals were once dismissed as impossible not because we lacked the technology to create them, but because we lacked the imaginative flexibility to conceive of them. They existed in the gap between what mathematics permitted and what our intuitions about causality and entropy allowed us to imagine possible. Imagine a particle detector sitting in a laboratory, measuring the behavior of photons as they pass through a barrier, and then, days or weeks later, a scientist makes a choice about how to configure that same detector retroactively. And somehow, impossibly, the measurements recorded in the past shift to match the future decision that hadn't been made yet. This is the foundation of retrocausality experiments, particularly those inspired by delayed choice quantum eraser setups and more recent work by researchers like John Wheeler, where the act of observation in the future appears to collapse wave functions that occurred in the past, suggesting that causality itself might flow backward through time under specific quantum conditions. These experiments genuinely work in repeatable, peer-reviewed laboratory settings, demonstrating that particles seem to behave as though they know what measurement awaits them, adjusting their historical behavior based on choices made after their initial detection, fundamentally challenging our assumption that effects must follow causes in a linear temporal sequence. The mechanism behind this phenomenon remains profoundly mysterious, though physicists have proposed that quantum entanglement creates connections between particles that transcend time itself, or that the universe operates in a way where all moments exist simultaneously, and measurements simply reveal correlations that have always been present in a deeper mathematical structure we call the wave function. What makes this genuinely unsettling is not merely that such experiments occur in laboratories, but that they reveal something broken about our most basic intuitions regarding how reality must function. Yet we have integrated them into physics curricula and accepted them as normal parts of quantum mechanics, despite the fact that retrocausality violates everything our evolutionary psychology told us about causation, precedence, and the arrow of time. We continue publishing papers about it, teaching it to students, and casually discussing backward causation as though it were merely another interesting physical principle rather than a fundamental crack in our understanding of existence itself. Yet perhaps this very casualness, this ability to compartmentalize the impossible, is itself the most revealing phenomenon. That we have become so skilled at absorbing paradoxes that we no longer experience genuine vertigo at the suggestion that reality might not unfold in time the way our consciousness insists it must, and that this adaptation may itself be the most profound discovery of all, revealing not something new about physics, but something long hidden about the malleable nature of human understanding itself. Perhaps this is why we so readily accept retrocausality in the quantum realm while remaining deeply unsettled by the mere suggestion of it in everyday life. Because accepting it requires us to surrender the illusion of agency, to acknowledge that the future and past are not separate territories, but rather different angles of view on a single, timeless landscape where our choices and observations are less like causes and more like acts of recognition, revealing what was always there, waiting to be seen. In the 1964, physicist John Bell proved something that should have shattered our understanding of reality itself, yet most people have never heard of it, and those who have often misunderstand what it actually means. Bell's theorem demonstrated mathematically that no theory of reality based on local hidden variables could ever reproduce all the predictions of quantum mechanics, and subsequent experiments have repeatedly confirmed that nature violates Bell's inequalities in ways that are fundamentally incompatible with the idea that objects have definite properties independent of measurement. What this means, stripped of mathematical language, is that either the universe is non-local, meaning distant parts of it can instantly influence each other in ways that seem to violate Einstein's speed of light limit, or reality itself does not exist in a definite state until something observes it, or some combination of both possibilities must be true. The experiments themselves are elegant and reproducible. Researchers take pairs of entangled particles, separate them by great distances, perform measurements on one particle that instantly seem to affect the properties of the other, and record correlations that are stronger than any local theory could possibly allow. The psychological mechanism that allows us to continue functioning despite this revelation is a form of compartmentalization so profound that we have essentially created two separate branches of human knowledge. One for the quantum realm where these bizarre rules apply, and one for everyday life where classical physics works perfectly well. We have normalized the idea that reality fundamentally operates on two incompatible principles depending on the scale we are examining, treating it as a solved problem rather than a profound mystery that should make us question the nature of existence itself. Physicists developed interpretations like the Copenhagen interpretation or many worlds theory to make sense of it, but these interpretations themselves raise questions more unsettling than the original problem, forcing us to accept either that consciousness plays a role in collapsing reality into definite states, or that every possible outcome actually occurs in branching universes. The most disturbing aspect is that we have decided this is simply how the universe works and have moved forward, building quantum computers and engineering technologies based on principles that still seem to violate basic logic, all while barely acknowledging the philosophical horror at the foundation of our modern understanding of the cosmos. Yet when a physicist successfully uses quantum entanglement to transmit information or develop a new cryptographic system, we celebrate the application while carefully avoiding deeper questions about what entanglement reveals about causality, determinism, and whether the universe itself might be fundamentally indifferent to our need for coherent explanations. The irony is particularly sharp when we consider that Bell's theorem itself was born from Einstein's discomfort with quantum mechanics, his conviction that God does not play dice with the universe, yet the universe appears to have answered by showing us that not only does it play dice, but the dice are fundamentally non-local and may not even exist until they are rolled. In the late 1980s, physicists John Bell and later Elaine Aspect conducted experiments that fundamentally challenged our understanding of how reality operates at its most basic level, demonstrating that particles separated by vast distances could instantaneously influence one another in ways that seem to violate the principle that nothing can travel faster than light, a phenomenon known as quantum entanglement or non-locality. When two particles become entangled, measuring a property of one particle instantaneously determines the corresponding property of the other particle regardless of the distance between them, whether they are separated by a few meters or by the entire width of the observable universe, and this correlation occurs faster than any signal could theoretically travel between them. The mechanism behind this strange reality operates through what physicists describe as a shared quantum state, a mathematical description of the system that encompasses both particles simultaneously until measurement occurs, at which point the wave function collapses and both particles conform to the measured values, suggesting that reality at the quantum level does not consist of independent objects with definite properties, but rather an interconnected whole where distant regions share an instantaneous relationship. What makes this situation even more peculiar is that we cannot use this non-local connection to send information faster than light, because the outcome of any individual measurement appears random and only becomes correlated when the results are compared through classical communication channels, meaning the apparent violation of causality is hidden behind the veil of randomness and the inability to control measurement outcomes. Despite decades of increasingly sophisticated experiments confirming these findings again and again, and despite the fact that Bell tests have closed nearly every possible loophole that skeptics could imagine, non-locality remains deeply counterintuitive, and most people continue living their daily lives operating under the assumption that reality is fundamentally local and that objects exist as independent entities with definite properties. Perhaps because accepting non-locality requires abandoning centuries of philosophical assumptions about the separability and independence of physical objects, and the notion that physical influence requires some kind of mediating signal or force. Yet this counterintuitive discovery has profound implications for how we understand the nature of space, time, and causality itself, suggesting that the universe may be fundamentally non-separable at its deepest level, with distant events connected through a web of correlations that transcends our classical intuitions about locality and independence. This realization has begun to reshape fields beyond physics, influencing how philosophers and scientists think about consciousness, information theory, and even the fundamental nature of observation itself. While technological applications like quantum computing and quantum cryptography are already leveraging these non-local correlations to achieve computational and security advantages impossible in classical systems. Consider the fundamental architecture of matter itself, the invisible law that literally prevents you from passing through a wall, and yet this law exists not because of force or energy, but because of something far stranger, a mathematical prohibition rooted in the quantum realm. Wolfgang Pauli discovered in 1925 that no two electrons can occupy the same quantum state simultaneously, and this principle extends to all fermions, the particles that make up all ordinary matter in the universe, creating an absolute barrier that nothing can overcome, not through force, not through pressure, not through any conceivable mechanism. When you place your hand against a table, you do not actually touch the table in any classical sense. Instead, the electron clouds surrounding the atoms in your hand repel the electron clouds surrounding the atoms in the table through this quantum prohibition, and the sensation of contact is entirely the result of this electromagnetic barrier created by particles forbidden from being in the same place at the same time. This principle is so fundamental that it determines the structure of atoms, the arrangement of electrons in shells, the properties of every chemical element, and ultimately the possibility of chemistry itself. Without it, electrons would collapse into the nucleus, atoms would not exist, molecules would not form, and the universe would be a fundamentally different place, perhaps no place at all. The psychological mechanism that normalizes this absurdity is our complete inability to perceive the quantum substrate beneath everyday experience. We feel solid surfaces and experience tangible resistance, so we construct mental models of contact and collision that operate at human scales, never glimpsing the actual mechanism generating these sensations, never truly confronting the fact that matter is mostly empty space held apart by mathematical rules rather than physical walls. We have built an entire civilization, an entire scientific framework, and an entire understanding of reality upon this principle without ever questioning why nature should enforce such a bizarre restriction, why the universe should care whether two particles occupy the same quantum state, or what mechanism could possibly prevent it if not some deeper law we have yet to discover. Leaving us in the strange position of using a principle we do not fully understand to explain the very solidity of the ground beneath our feet. And yet this mystery deepens when we consider that the principle itself cannot be derived from more fundamental laws. It stands as an axiom of quantum mechanics, a brute fact of nature that we accept because it works, because it predicts with stunning accuracy everything from the periodic table to the behavior of neutron stars, suggesting that some truths about reality may be too fundamental to explain, existing not as consequences of deeper physics, but as the bedrock upon which all deeper physics must be built. This acceptance of mystery as foundation is perhaps the deepest lesson of modern physics, that the universe grants us the privilege of understanding its mechanisms without necessarily revealing the reasons behind them, and in this humility before the unknowable, we find not frustration but a kind of wonder, the recognition that consciousness itself, governed by quantum processes in the neurons of our brains, emerges from the very prohibition that keeps us from falling through the floor. At the smallest scales of reality, particles exist in what physicists call superposition, a state where they simultaneously occupy multiple positions, spin states, or energy levels until the precise moment they are observed or measured, at which point this quantum fog collapses into a single definite state that we can actually detect and record. This is not merely a limitation of our measurement tools or our inability to see what is truly happening beneath the surface, but rather appears to be a fundamental feature of how reality itself operates at the quantum level, where electrons can be here and there at the same time, where a particle can spin both clockwise and counterclockwise simultaneously, and where a quantum system literally has no determined properties until interaction forces it to choose. The implications are staggering because this suggests that the universe does not consist of fixed, predetermined objects with intrinsic properties waiting to be discovered, but rather exists as a collection of potentialities and probabilities that only crystallize into concrete reality through the act of observation itself. Meaning, in some profound sense, the observer participates in creating the universe rather than merely recording it as it already exists. Yet, despite over a century of experimental verification, despite countless demonstrations in laboratories worldwide, and despite the fact that quantum superposition forms the mathematical bedrock of technologies like computers and lasers that we use every single day, we continue to navigate our lives as though classical reality is somehow more fundamental. As though the world of solid objects with definite positions and properties is the ground truth, while quantum mechanics is merely an abstract theory about tiny things that do not really matter to our lived experience. We have essentially normalized one of the most bizarre and logically troubling discoveries in the history of human knowledge by compartmentalizing it, by treating it as something that applies only to laboratories and particle accelerators and quantum computers, rather than acknowledging that superposition is the actual foundation upon which all larger structures, including our own bodies and brains, are ultimately constructed and sustained. And this cognitive separation allows us to sleep peacefully while harboring a contradiction at the very heart of our understanding of existence itself. The atoms in your hand exist in superposition as you read these words, their electrons distributed across probability clouds rather than occupying fixed orbits, and yet your hand feels solid, continuous, and real. A masterclass in how emergent classical behavior arises from quantum foundations, even as the deeper truth of what you are remains fundamentally uncertain, until the universe, in its relentless way, continues to observe itself into being. Perhaps this is why quantum mechanics remains so philosophically unsettling, not because it is wrong, but because it refuses to let us maintain the comfortable illusion that observation is a passive act, that consciousness merely witnesses a world that exists independent of it, when in fact the very fabric of reality appears to require participation, interaction, and the collapse of infinite possibilities into the singular facts we call experience. In the quantum realm, particles behave in a manner that defies our everyday intuition about how objects should exist and move through space, operating according to principles that seem fundamentally at odds with the classical physics we observe in the macroscopic world. According to quantum mechanics, particles do not have definite positions until they are measured or observed, meaning that an electron, photon, or any other subatomic particle exists in what physicists call a superposition state, essentially occupying all possible positions simultaneously across a given space, until the act of measurement forces it to collapse into a single, definite location. This phenomenon, which emerges from the mathematical frameworks of wave functions and probability distributions, suggests that before observation, a particle is not simply moving in a trajectory we cannot see, but rather genuinely exists in a kind of probabilistic cloud distributed across regions of space with varying degrees of likelihood. The implications become even stranger when we consider that particles can tunnel through barriers that classical physics says should be impenetrable, appearing on the other side of obstacles without ever traversing the space between, or that two entangled particles can influence each other instantaneously across arbitrary distances as though space itself is no barrier to their connection. What makes this particularly difficult to reconcile is that we have built our understanding of reality on the assumption that objects exist in specific places at specific times, that they move through space in continuous paths, and that cause and effect propagate at finite speeds. Yet the quantum world operates under entirely different rules, and these rules have been verified countless times through experimental evidence that continues to hold up under scrutiny. Despite decades of successful predictions and technological applications built upon quantum mechanics, we have never truly resolved the conceptual problem of how reality can function this way, how particles can exist everywhere and nowhere until observed, how the universe can be fundamentally probabilistic at its foundation and yet appear deterministic and orderly to us. We have learned to accept this as mathematical truth, to work with the equations and make predictions, yet a deep unease remains about what this actually means for the nature of existence itself. Perhaps the most unsettling aspect is that this probabilistic foundation doesn't merely describe our ignorance of particle behavior. It suggests that uncertainty and indeterminacy are woven into the fabric of reality itself, that the universe genuinely doesn't decide where a particle is until that moment of observation collapses infinite possibilities into singular fact. This realization challenges not just our physics but our philosophy. If observation itself plays a role in determining reality, then the boundary between observer and observed becomes dangerously blurred, raising the question of whether consciousness or measurement are fundamental forces in the universe, or whether we are simply witnessing nature's way of encoding information across space in ways our classical minds struggle to comprehend. Deep within the fabric of quantum mechanics exists one of the most perplexing phenomena that physicists have had to accept as fundamental to reality itself, and that phenomenon involves particles that should not exist but demonstrably do, emerging from absolute nothingness for infinitesimally brief moments before vanishing back into the void from which they came. These entities, known as virtual particles, represent a category of subatomic constituents that pop into existence within the quantum vacuum without any apparent cause or mechanism, existing only for durations so impossibly short that they violate the conservation of energy in ways that classical physics would declare completely impossible. Yet they do so consistently and predictably enough that they have become woven into the very equations that describe how the universe operates at its most fundamental level. The quantum vacuum, which most people intuitively understand as empty space devoid of any substance or activity, is actually a seething foam of ceaseless activity where particle-antiparticle pairs spontaneously emerge, interact briefly, and then annihilate each other in a cosmic game of creation and destruction happening at scales too small and durations too brief for any human instrument to directly observe individual events. These virtual particles are not theoretical abstractions or mathematical conveniences introduced for the sake of making equations work. Rather, they produce measurable, observable effects in the physical universe, such as the Casimir Effect, where two uncharged metal plates placed extremely close together experience an attractive force that can only be explained by the presence of virtual particles whose population differs between the plates and the surrounding space. The psychological mechanism that allows physicists and the broader scientific community to accept this reality involves a profound epistemological shift, where we have learned to define existence not by direct observation, but by measurable consequences and effects, meaning that if something produces detectable outcomes and appears consistently in our mathematical frameworks, we grant it the status of real regardless of whether we can perceive it directly or understand it intuitively. What makes this phenomenon particularly strange is not merely that particles emerge from nothing and disappear, but that this process occurs everywhere simultaneously across all of space at all times, an infinite number of creations and annihilations happening in every cubic centimeter of vacuum every microsecond. Yet we have so thoroughly normalized this concept within modern physics that it appears in textbooks alongside other accepted phenomena with barely a hint of the conceptual vertigo it should inspire. We have accepted that reality operates according to rules where nothingness is never truly nothing, where empty space is not empty, and where particles can borrow existence from the universe itself, provided they repay that debt quickly enough that the mathematics allows it. All while maintaining a scientific demeanor that treats this as simply another aspect of how nature works, rather than a fundamental indication that our deepest understanding of existence might be incomplete, or that we are describing something that transcends our conventional notions of reality and causality. In 1948, Dutch physicist Hendrik Casimir proposed something that should be impossible according to conventional understanding of the universe, yet it has been measured, verified, and continues to baffle physicists today. He theorized that two uncharged metal plates placed extremely close together in a perfect vacuum would experience an attractive force pushing them toward each other, not because of any conventional electromagnetic interaction or gravity, but because of the quantum foam that supposedly underlies all of reality. According to quantum field theory, empty space is not actually empty at all, but rather seethes with virtual particles constantly appearing and disappearing in infinitesimal fractions of time, and between two metal plates positioned close enough together, fewer of these virtual particles can exist than in the space outside the plates, creating a pressure differential that literally pushes the plates together with measurable force. This phenomenon, now called the Casimir Effect, has been experimentally confirmed numerous times, with researchers detecting attractive forces that match Casimir's calculations with remarkable precision, meaning that nothing, not even the complete absence of matter and energy, is truly empty or inert. The mechanism behind this reality-bending effect involves understanding that quantum field theory permits these virtual particle pairs to spontaneously emerge from the vacuum and annihilate each other almost instantaneously. And the presence of physical boundaries like metal plates constrains which wavelengths of these quantum fluctuations are allowed to exist between them, while outside the plates the full spectrum of possible fluctuations can occur unimpeded. What persists despite seeming conceptually impossible is our casual acceptance that the vacuum itself possesses energy, that nothing is fundamentally different from something, and that the universe contains hidden forces and structures that can only be described using mathematics rather than intuition. Yet we treat this as settled science, rather than acknowledging the profound strangeness of accepting that empty space pushes objects around with real, measurable force. The implications extend beyond mere laboratory curiosity. The Casimir effect suggests that vacuum energy might be harnessed for propulsion systems, that the structure of spacetime itself could be manipulated, and that our universe operates according to principles so counterintuitive that we may have barely begun to grasp the true nature of reality beneath the surface of observable phenomena. Some theorists have speculated that the Casimir effect might even play a role in the mysterious dark energy that appears to be accelerating the expansion of the universe itself, suggesting that what we observe on the grandest cosmic scales could be influenced by the same quantum vacuum fluctuations measured between metal plates in laboratories on Earth. If true, this would mean that the smallest phenomena and the largest structures in existence are fundamentally connected through the same bewildering physics. At the heart of quantum mechanics lies a concept so strange that it seems to violate everything we understand about energy and conservation. The idea that empty space itself contains infinite energy, a seething quantum foam that permeates every cubic centimeter of the universe, even in the absence of matter or particles. This phenomenon, known as zero-point energy, refers to the residual kinetic energy that atoms and molecules possess even when cooled to absolute zero, the theoretical lowest possible temperature, and it emerges from the fundamental uncertainty principle that prevents particles from ever truly being stationary. The vacuum of space, far from being empty, is theorized to contain virtual particle pairs constantly popping in and out of existence, annihilating each other almost instantaneously, yet leaving behind measurable effects that physicists have confirmed through experiments like the Casimir Effect, which demonstrates that the quantum vacuum does indeed exert a measurable force between two uncharged metal plates held in close proximity. For decades, scientists and inventors have speculated wildly about harnessing this energy, imagining it as a limitless source of power that could revolutionize human civilization, solve the energy crisis, and provide unlimited clean electricity to every corner of the world. Yet despite the compelling theoretical foundation, we remain unable to extract or utilize this energy in any practical way. The psychological mechanism driving the persistence of zero-point energy enthusiasm stems from a profound human tendency to believe that science has revealed hidden layers of reality that contradict our intuitions, combined with the legitimate fact that quantum mechanics is genuinely counterintuitive, and that most people lack the mathematical expertise to fully understand it, creating a fertile ground where speculation can flourish and blend with legitimate physics. What makes this particularly remarkable is how the concept has become normalized within both fringe science communities and mainstream culture as something that is being actively suppressed or hidden rather than simply remaining technically impossible, suggesting that we have constructed an elaborate belief system around the idea that our understanding of physics contains a secret loophole that only certain individuals have recognized. Even though the scientific consensus remains that while zero-point energy exists theoretically, the laws of thermodynamics prevent us from tapping into it in any meaningful way. Yet this distinction between theoretical existence and practical inaccessibility rarely penetrates popular consciousness, where zero-point energy devices continue to be reinvented and marketed with the same promises of unlimited power, each iteration capturing the imagination of those who sense that mainstream science must be missing something fundamental about how reality works. The irony, of course, is that zero-point energy represents not a failure of physics, but rather a triumph of it, a theory so robust and mathematically elegant that it successfully predicts phenomena across scales from subatomic particles to the expansion of the universe itself, making the very impossibility of harnessing it a feature rather than a bug, a humbling reminder that understanding reality and controlling it remain fundamentally different enterprises. Imagine if you calculated the energy density of empty space itself, the vacuum energy that theoretically should permeate every cubic centimeter of the universe, and then compared it to what observations actually show us, you would discover something profoundly unsettling. The predicted value is roughly 120 orders of magnitude larger than what we measure, a discrepancy so staggering that it defies rational comprehension and has been called the worst prediction in the history of theoretical physics. When physicists in the 1980s began taking quantum field theory seriously and attempted to calculate the energy of nothingness, they found that virtual particles constantly popping in and out of existence should contribute an enormous amount of energy to the vacuum. Yet when astronomers observed distant supernovae and measured how the universe's expansion was behaving, they discovered that empty space appears to have only a tiny amount of energy, small enough that it barely affects cosmic expansion at all, creating a gap between prediction and observation so wide that it suggests something fundamental about our understanding of reality is deeply wrong. The mechanism behind this discrepancy lies in the way we separate different scales of physics. Quantum mechanics tells us one thing should happen at the smallest scales, while general relativity tells us something entirely different should happen at the largest scales. And when we attempt to unite these two pillars of modern physics, the mathematics produces a vacuum energy density that is absurdly, impossibly, inexplicably large compared to what we actually see in the cosmos. What makes this problem so peculiar is that physicists have largely normalized the inability to solve it, proceeding with their work despite the fact that the most fundamental calculation about the nature of empty space is wildly incorrect by more than a factor that the human mind struggles even to conceptualize, treating it as a mysterious fine-tuning of nature rather than an indicator that something crucial is missing from our theoretical framework. And this acceptance of profound ignorance at the heart of cosmology continues to perplex those who recognize that any such enormous discrepancy should demand urgent revolutionary changes to how we think about space, time, energy, and existence itself. Perhaps the deepest irony is that we have named this unknown energy dark energy and assigned it 70% of the universe's total mass energy content, effectively admitting that the cosmos is dominated by something we cannot explain. Yet we continue building our cosmological models around this placeholder rather than questioning whether our fundamental assumptions about quantum fields and spacetime curvature might themselves require reconstruction from the ground up. The problem becomes even more acute when we consider that if the cosmological constant were larger by even 1 part in 10 to the 53rd power, the universe would have either collapsed immediately after the Big Bang or expanded so rapidly that stars and galaxies could never have formed, suggesting that either we are the beneficiaries of an impossibly unlikely cosmic lottery, or the very framework through which we calculate vacuum energy requires fundamental reconsideration that may reshape our understanding of quantum mechanics and gravity alike. One of the most troubling anomalies in modern cosmology is something called the Hubble Tension, a mysterious discrepancy in measurements that has forced physicists to confront the possibility that something fundamental about our understanding of the universe might be wrong. The Hubble constant is essentially the rate at which the universe is expanding, named after astronomer Edwin Hubble, and for decades scientists have attempted to measure it using two independent methods that should theoretically yield identical results. The first method involves observing distant supernovae and measuring how fast they appear to be moving away from us, while the second method uses the cosmic microwave background, the ancient light left over from the Big Bang, combined with measurements of how the universe's geometry relates to its expansion rate. When researchers performed these calculations with increasingly precise instruments and data, something deeply unsettling emerged. Two methods consistently produced different answers, and the discrepancy was far too large to be explained by measurement error or statistical coincidence. One method suggested the universe was expanding at approximately 67 kilometers per second per megaparsec, while the other indicated it was expanding at approximately 73 kilometers per second per megaparsec, a difference of roughly 9% that persists no matter how carefully scientists refine their observations. This tension exists because both measurement techniques are rooted in well-tested physics and both employ rigorous methodology, yet they cannot both be correct, implying either that one method is fundamentally flawed in ways we have not yet discovered, or that our deeper understanding of cosmic expansion, dark energy, or even the very nature of spacetime itself contains a hidden error. The psychological mechanism that allows this contradiction to persist is the same mechanism that allows scientists to continue their work despite such profound uncertainty. Rather than paralysis, physicists have learned to treat the Hubble tension as a productive puzzle, a motivating anomaly that drives new research rather than one that shatters confidence entirely. We have normalized the idea that reality can contain genuine contradictions that resist easy resolution, and instead of abandoning our models, we simply add the tension to a growing list of cosmic mysteries that future discoveries might illuminate, effectively learning to live within scientific uncertainty while maintaining faith that deeper truths await. Some physicists speculate that the resolution might require exotic modifications to our theories. Perhaps dark energy behaves differently than we assumed, or perhaps the universe's expansion rate has genuinely changed in ways our models fail to capture, while others remain convinced that we simply have not yet identified a subtle systematic error in one of our measurement techniques. A humbling reminder that even our most precise instruments can deceive us in ways we do not yet comprehend. What makes the Hubble tension particularly humbling is that it may ultimately reveal not a flaw in our instruments or methods, but rather the limits of our current theoretical framework, suggesting that the universe operates according to principles we have yet to discover, principles that might only become visible once we abandon our certainty about how expansion itself should work. When astronomers observe distant galaxies through our most powerful telescopes, they discover something that appears to violate the fundamental laws of physics that we have built our understanding of the universe upon, which is that nothing can travel faster than the speed of light. Yet the data consistently shows that galaxies at the far reaches of the observable universe are moving away from us at velocities that exceed the speed of light itself, with some reaching speeds of multiple times light speed, depending on their distance from Earth. This phenomenon is not actually a violation of Einstein's special relativity, because the galaxies themselves are not moving through space faster than light, but rather space itself is expanding between us and those distant galaxies at an accelerating rate, which means the metric of space is stretching and creating distance faster than photons could ever traverse it. A distinction that allows the mathematics to remain consistent, while the observable reality still challenges our intuitions about how reality should function. The mechanism behind this expansion is driven by something called dark energy, a mysterious force that comprises approximately 68% of the entire universe and works in opposition to gravity, pushing the fabric of spacetime apart in all directions simultaneously, and the further away a galaxy is from our position, the more space exists between us and it, meaning the velocity of recession increases with distance, which is known as Hubble's law and creates this strange situation where distant galaxies can appear to move away from us faster than light, while technically not violating the cosmic speed limit. What persists most strikingly is how we have accepted this explanation as normal despite the fact that it requires us to accept the existence of dark energy, an invisible substance that we cannot directly detect or fully understand, making up the majority of the universe while remaining fundamentally mysterious. And yet this explanation has become so embedded in our scientific understanding that we rarely pause to consider how extraordinary it is that the universe is mostly composed of something we cannot see, cannot touch, and cannot explain, and that the very fabric of reality is expanding at an accelerating rate in ways that seem almost designed to confound our ability to fully comprehend our cosmic surroundings. Yet perhaps this very mystery is what makes the discovery so profound. that we have mapped the universe's expansion well enough to predict its future, even as the engine driving that expansion remains hidden from us, suggesting that sometimes understanding the rules of reality requires us to accept that we may never fully comprehend the deeper mechanisms beneath them. And in this acceptance lies perhaps the greatest lesson of modern cosmology, that the universe is under no obligation to conform to our expectations, and that our willingness to revise our understanding in the face of evidence, even when that evidence points to something we cannot directly observe, remains the most powerful tool we possess for deciphering the cosmos's deepest secrets. When we look up at the night sky, our intuition screams that we are standing at a special place, a privileged vantage point from which to observe the cosmos, yet the truth that emerges from modern cosmology is far stranger and more unsettling than our ancestors ever imagined. The universe, according to our best scientific understanding, has no center at all, which means there is no privileged location, no cosmic throne from which creation emanates, and no objective way to declare any point more important or special than any other. This revelation contradicts something so fundamental to human perception that we have spent centuries trying to prove it wrong, clinging to models that placed Earth at the center, then our sun, then our galaxy, always searching for that one location that would justify our intuitive sense of being somewhere meaningful. The expansion of space itself, as discovered through observations of distant galaxies moving away from us in all directions, initially appeared to suggest we occupied a central position, yet this same pattern would be observed from any location in the universe, because the expansion is not occurring through space, but rather of space itself, stretching the fabric between all objects equally. Our minds resist this notion because evolution never prepared us to understand infinite, homogeneous systems without boundaries or preferred locations. We evolved in environments with obvious centers, horizons, and special places, which encoded itself deeply into how we process reality. The psychological mechanism at work here involves what we might call positional bias, a fundamental inability to comprehend that our location is truly arbitrary, that there is nothing cosmically or physically special about the particular vantage point from which we observe the universe, and that this is not a deficiency in our understanding, but rather the actual nature of reality itself. What makes this truth persist in our collective consciousness, despite having been scientifically established for decades, is that it contradicts our visceral, embodied experience of the world, and we continue to think and speak in ways that implicitly assume centers, directions, and special locations, even as we intellectually accept that none of these things truly exist on a cosmic scale. Yet paradoxically, this absence of cosmic hierarchy may be the most profound equalizer ever discovered. It suggests that consciousness, meaning, and observation arise not from special positions, but from the universal capacity of matter to organize itself into observers, a capacity that exists potentially everywhere and nowhere simultaneously. If this is true, if we are not special, then perhaps the question we should ask ourselves is not why we exist in this particular location, but rather why existence itself generates the illusion of centeredness in every conscious being that arises within it, a cosmic joke in which every perspective, no matter how humble or remote, experiences itself as standing at the heart of everything. This paradox reveals something essential about consciousness itself. The view from nowhere is experienced as the view from everywhere, and in that universal shareability of perspective lies, perhaps, the deepest democracy the cosmos could offer, where a human gazing upward from Earth stands on precisely equal footing with whatever observers might emerge on distant exoplanets or in the far reaches of spacetime yet to unfold. When cosmologists peer into the deepest structures of reality, mapping the cosmic microwave background radiation with extraordinary precision, they consistently arrive at a conclusion that seems to contradict our intuitive understanding of three-dimensional space. The universe, when measured at the largest scales, appears to be geometrically flat. This flatness refers not to pancake-like configuration, but rather to the curvature of spacetime itself, and the observations suggest that the universe contains almost exactly the right amount of matter and energy to produce zero overall curvature, a condition so mathematically improbable that it seems almost deliberately engineered. The precision of this flatness is staggering. Measurements indicate the universe's geometry deviates from perfect flatness by less than 1%, a number so small that it has puzzled physicists for decades because the probability of such precise balance occurring randomly should be vanishingly tiny. This discovery emerged from decades of increasingly sensitive measurements, particularly from observations of how light from distant supernovae behaves and how the cosmic microwave background radiation fluctuates across the sky, with each successive observation confirming that our universe really does appear to be flat rather than curved like a sphere or saddle. The psychological mechanism that allows this reality to persist in our scientific understanding, despite its counterintuitive nature, lies in the compartmentalization of scales. We experience a curved, three-dimensional world at human scales, and that sensory experience remains stubbornly resistant to abstract mathematical correction. So we accept the flatness as a mathematical property of the universe's overall structure, while simultaneously maintaining our everyday understanding of spatial relationships. Scientists and educated people have normalized this strange duality by treating cosmic geometry as a separate category of knowledge, one that operates according to relativistic principles rather than Euclidean intuition, creating a mental framework where flatness becomes simply another surprising feature of reality rather than a profound contradiction requiring resolution. The universe manages to be flat, expanding, and filled with matter and dark energy all at once, a combination so delicately balanced that physicists invoke mechanisms like cosmic inflation to explain why the initial conditions were so precisely tuned. Yet we discuss this extraordinary circumstance with the same casual tone we might use to describe any other astronomical measurement. The flatness paradox exemplifies how modern cosmology has learned to embrace profound mysteries without requiring immediate answers. We measure the universe's geometry with confidence while remaining genuinely uncertain whether this flatness is fundamental to reality, a consequence of inflation, or perhaps evidence of physics operating at scales we cannot yet perceive. What remains clear is that this geometric property of the cosmos, this improbable flatness, stands as one of the most productive mysteries in physics, driving theoretical innovations from inflation theory to explorations of multidimensional geometry, while simultaneously reminding us that the universe's deepest truths often emerge not from intuition, but from the patient accumulation of precise measurements that gradually reshape our understanding of what is possible. In 2002, President George W. Bush stood before Congress and defined three nations as constituting an axis of evil: Iraq, Iran, and North Korea, a phrase that would reshape global politics and justify military intervention for years to come. The term borrowed deliberately from the Axis powers of World War II, creating an immediate psychological parallel between contemporary geopolitical adversaries and history's most destructive alliance. Yet the actual connections between these three nations were tenuous at best, almost non-existent in practice. Iraq under Saddam Hussein was a secular Arab state. Iran was a theocratic Islamic republic with deep historical grievances against Iraq. North Korea was a communist authoritarian regime isolated on the Korean peninsula with virtually no meaningful diplomatic or military alliance with either of the other two. These three countries shared no unified ideology, no coordinated military strategy, no common economic interests, and in many cases actively opposed one another's regional ambitions. What they did share was their designation as enemies of American foreign policy interests. Yet by grouping them under a single categorical framework, the Bush administration created a narrative structure that simplified complex geopolitical realities into a comprehensible moral binary of good versus evil. The psychological mechanism at work here involves what cognitive scientists call categorical thinking, our tendency to organize disparate elements into unified groups based on a single dominant characteristic, which then allows us to apply uniform judgments and responses to all members of that category regardless of their actual differences. By naming these nations as an axis, the administration activated centuries of historical memory associated with World War II's Axis powers, while simultaneously suggesting a coordinated threat that justified preemptive military action, surveillance programs, and international isolation. What remains extraordinary is how this rhetorical construction persisted and shaped policy despite lacking empirical support. No weapons of mass destruction were ever found in Iraq. No evidence emerged of the coordinated threat the phrase implied, yet the categorization had already accomplished its psychological work on the American public and international community. We continue to operate within frameworks of thought that were constructed for strategic communication purposes rather than descriptive accuracy, accepting the residual effects of language designed to justify specific political actions, demonstrating how powerfully naming and categorization can override observable reality. The invasion of Iraq in 2003, launched partly on premises that would later prove false, killed hundreds of thousands, and destabilized an entire region. Yet the linguistic frame that enabled it remains largely unexamined in our collective memory, a testament to how successfully language can substitute for evidence and how reluctant we are to interrogate the foundational narratives that guide our most consequential decisions. The phrase itself has outlived its utility as policy justification, yet persists in political discourse, a linguistic ghost that continues to organize how we perceive threats and legitimize interventions, while those who benefited from its rhetorical power face minimal accountability for the consequences of their carefully constructed narratives. Deep within the cosmic microwave background radiation that fills the entire universe, a peculiar anomaly has been observed by astronomers and cosmologists for decades, a region of space that should theoretically contain the same temperature and density as every other part of the ancient light that has been traveling toward us since the Big Bang itself. Yet instead there exists an area roughly 2% colder than the surrounding radiation. A spot so anomalous that it spans about 10% of the entire sky and refuses to be adequately explained by our current understanding of physics and cosmology. The cosmic microwave background radiation represents the oldest light in the universe, released approximately 380,000 years after the Big Bang, when the universe finally cooled enough for electrons and protons to combine into neutral atoms. And this ancient light has been stretching and cooling ever since, arriving at Earth as a uniform bath of microwave radiation at a temperature of roughly 2.7 Kelvin. But this uniformity is interrupted by the cold spot, a region discovered through satellite observations where the radiation measures noticeably dimmer and cooler than the statistical average. Scientists initially proposed that the cold spot might be explained through ordinary cosmic structures, perhaps a massive void in the distribution of matter and energy, or a region of space where fewer galaxies exist, which would theoretically produce cooler radiation signatures through gravitational lensing effects. Yet when researchers conducted surveys of the cold spot region using multiple wavelengths and observational methods, they found that the traditional explanations fell short of accounting for the full magnitude of the anomaly, suggesting that something more exotic might be occurring at the largest scales of cosmic structure. The persistence of the cold spot, despite having no satisfactory conventional explanation, has led some researchers to propose increasingly speculative theories, including the possibility that our universe exists within a larger multiverse, and that the cold spot represents a bruise or impact scar from collision with another universe during the inflationary epoch, or that we are observing the signature of topological defects in spacetime itself. Defects that might have formed during phase transitions in the early universe, yet none of these hypotheses have achieved the status of accepted theory because they require physics beyond what has been experimentally verified. And so the cold spot remains an enduring mystery that has normalized the concept of large-scale cosmic anomalies that we cannot fully explain, a reminder that despite our sophisticated instruments and mathematical models, the universe continues to present us with phenomena that resist easy categorization and force us to confront the limits of our current cosmological understanding. Future observations from next-generation telescopes and more precise satellite measurements may eventually reveal whether the cold spot represents a genuine departure from cosmological principles or merely a statistical fluctuation that appears anomalous only when viewed through the lens of our current theoretical frameworks, a distinction that will ultimately determine whether we must fundamentally revise our understanding of cosmic origins and structure. In the vast cosmic expanse beyond what our telescopes can directly observe, astronomers have detected something profoundly unsettling, a mysterious gravitational pull dragging entire galaxy clusters toward a region of space they call the Great Attractor, located roughly 150 to 250 million light-years away in the direction of the Centaurus and Hydra constellations. But this discovery becomes even stranger when scientists analyze the motion more carefully, because they find that the Great Attractor itself appears to be moving, being pulled by something even more massive and distant, something so incomprehensibly enormous that it influences the structure of the universe at scales that dwarf our current understanding. Researchers have termed this phenomenon dark flow, referring to the persistent, directional motion of matter toward a region so distant and so obscure that it lies entirely beyond the observable universe's edge, existing in the theoretical realm of the cosmic horizon where our instruments simply cannot reach. The evidence comes from careful measurements of the cosmic microwave background radiation, those ancient photons left over from the Big Bang itself, which show subtle temperature variations and directional patterns, suggesting that our entire galaxy cluster is being gently but persistently pulled in a specific direction by gravitational forces originating from something we cannot see, cannot measure, and cannot directly prove exists. The psychological and conceptual mechanism here involves confronting the limits of human knowledge and our place within a cosmos far grander than we imagined, forcing us to accept that somewhere beyond our perception exists something massive enough to move billions of galaxies, yet we remain fundamentally ignorant of its nature, composition, or origin. We have normalized this cosmic mystery by relegating it to academic discussions and scientific papers, treating dark flow as merely another puzzle to eventually solve rather than as a profound statement about the limits of observation and understanding. Yet it persists as a genuine anomaly in our models of reality, a gravitational whisper from beyond the edge of everything we can ever know, reminding us that the universe contains forces and structures operating at scales where our intuition becomes meaningless and our instruments grow silent. Perhaps most humbling is that dark flow suggests the universe itself may possess structures and hierarchies we have barely begun to conceptualize. Vast walls and filaments of matter arrayed across distances so immense that even our most distant observations capture only a fragment of a grander cosmic architecture, leaving us to wonder what other invisible currents shape reality from beyond our perceptual horizon. And if dark flow exists, then the observable universe, that sphere of space roughly 93 billion light-years across that we consider our cosmic domain, may be merely a provincial backwater in a vastly larger reality, one of countless island universes all subject to gravitational influences from structures so remote and massive that they operate entirely outside our sphere of comprehension, suggesting that our most fundamental models of cosmic structure may be incomplete in ways we have yet to imagine. Deep within the cosmic structure of our universe exists a gravitational anomaly so massive and so powerful that it is literally pulling entire galaxies toward it at speeds of millions of miles per hour. And yet we cannot see it, we cannot photograph it, and we do not fully understand what it is. This phenomenon is called the Great Attractor, and it represents one of the most profound mysteries in modern astrophysics, a blind spot in our understanding of reality itself that challenges everything we believe we know about the distribution of matter in space. When astronomers began mapping the movements of galaxies in the 1980s, they discovered something deeply unsettling. Galaxies across an enormous region of space, spanning hundreds of millions of light-years, were all moving in the same direction with surprising uniformity, as if being pulled by an invisible hand toward a specific point in space, located roughly 240 million light-years away in the direction of the Centaurus and Norma constellations. The gravitational pull is so immense that it overcomes the expansion of the universe itself, that fundamental force which pushes everything apart. Yet when astronomers pointed their telescopes toward this region, they found far fewer galaxies than the gravitational signature suggested should exist. The mechanism behind this mystery involves the way gravity works across cosmic distances. Matter attracts matter through the curvature of spacetime, and the distribution of galaxies and dark matter throughout the universe should create a relatively smooth gravitational landscape. Yet instead we observe this concentrated pull toward an empty-seeming region, suggesting either that our maps of visible matter are incomplete, that dark matter is concentrated in ways we do not yet comprehend, or that some entirely unknown mass distribution exists beyond our current detection capabilities. What makes the Great Attractor particularly strange is how we have normalized its existence despite its fundamental inexplicability. Astronomers acknowledge it, include it in models, discuss it in academic papers, and yet continue their work as if we understand what is happening, when in reality we are observing evidence of something that should not be possible according to our current theories. The Great Attractor persists in our collective scientific consciousness as a phenomenon we accept without resolution, a cosmic force that reminds us that the universe may contain structures and mechanisms far beyond what our instruments and theories presently allow us to comprehend, and that some of the most powerful forces shaping the cosmos may remain forever hidden from our view. Perhaps most humbling of all is the possibility that the Great Attractor itself may be merely a local phenomenon, a small-scale gravitational feature within an even larger cosmic structure we have yet to detect, suggesting that our universe contains nested hierarchies of invisible architecture, each layer revealing new depths of complexity that recede forever beyond the horizon of human knowledge. Somewhere between the constellations of Boötes and Coma Berenices, in a region of space approximately 250 million light-years away from Earth, exists a cosmic void so profoundly empty that it challenges our basic understanding of how the universe should be distributed. The Boötes Void, as astronomers have named it, is a spherical region spanning roughly 240 million light-years in diameter, containing perhaps only 1/10 the number of galaxies that should theoretically exist in such a volume according to our current models of cosmic structure. This is not an empty space between galaxies, which would be unremarkable. This is an impossibly sparse region where the density of matter itself appears to have been fundamentally depleted, a cosmic desert so vast that it dwarfs anything we can experience or even properly conceptualize in human terms. When astronomers first discovered this void through systematic surveys of galaxy distributions, they were confronted with something that should not exist according to the cold dark matter models that have successfully predicted nearly every other feature of the large-scale universe. The prevailing understanding suggests that matter should be distributed relatively uniformly across cosmic scales, with only modest variations in density that grow into the cosmic web we observe today. Yet the Boötes Void persists as an outlier so extreme that it forces us to confront the possibility that our comprehension of cosmic structure remains incomplete. The mechanism behind this void's existence remains genuinely mysterious, with various hypotheses proposed including quantum fluctuations in the early universe, gravitational effects of unseen structures, or the possibility that we misunderstand how structures form at these scales. What makes the Boötes Void particularly unsettling is not merely its existence, but our collective acceptance of ignorance regarding it, the way we continue mapping the universe and cataloging its strangeness, while acknowledging that we have discovered something that should not be there according to everything we thought we understood about physics. We have normalized incomprehension itself, proceeding methodically forward in our surveys and observations while leaving the void as a persistent question mark, a reminder that the universe operates according to rules we have not yet fully grasped, and that somewhere in the darkness between stars, vast regions of near-absolute nothingness exist in defiance of our theories. Perhaps it is fitting that we have named this emptiness after Boötes, the ancient herdsman of the sky, a figure eternally pursuing something just beyond his reach, for in studying this void, we too chase understanding through a darkness that may never fully yield its secrets. And yet, each new survey, each incremental improvement in our observational instruments, returns the same haunting data. A region where galaxies should flourish remains stubbornly, inexplicably sparse, as if some fundamental principle of cosmic assembly has been suspended within those distant boundaries, leaving us to wonder what other voids might exist beyond our current detection threshold, waiting silently for us to finally develop the tools and the theoretical framework to understand them. In 2015, a star designated KIC 8462846, located approximately 1,400 light-years from Earth in the constellation Cygnus, began exhibiting behavior that defied conventional astronomical explanation and immediately captured the attention of researchers worldwide. Citizen scientists analyzing data from NASA's Kepler Space Telescope discovered that this star, which astronomers would subsequently nickname Tabby's star after lead researcher Tabitha Boyajian, was dimming in ways that had never been observed before, with the light reaching us from this distant sun fluctuating by as much as 20% over irregular intervals, creating a pattern so unusual and unpredictable that it suggested something massive was periodically blocking the starlight before it could reach our instruments. The conventional explanation for such dimming would typically involve an orbiting planetary body or debris field following a predictable, regular pattern that astronomers could easily model and understand. Yet Tabby's star exhibited none of this orderliness. instead displaying erratic dips in luminosity that seemed almost deliberately chaotic and resistant to categorization. When scientists first encountered these anomalies, they naturally considered and then systematically eliminated the most obvious possibilities, including instrumental errors, known astronomical phenomena, and standard stellar behavior, only to find themselves left with a mystery that forced them to consider more exotic and speculative explanations. The most captivating hypothesis proposed by some researchers involved the possibility of a Dyson swarm, a theoretical megastructure that an advanced civilization might construct around a star to harvest its energy, with countless orbiting panels or solar collectors gradually consuming the starlight before it escaped into space. This concept, rooted in serious physics and mathematics, yet profoundly science-fictional in its implications, represented humanity's willingness to consider that what we observe in the cosmos might reveal traces of intelligence far older and more technologically sophisticated than our own. Yet despite years of intensive study, sophisticated analysis, and continuous observation, no definitive explanation has emerged, and Tabby's star remains suspended in a state of genuine astronomical uncertainty. The remarkable aspect of this ongoing mystery lies not in the star itself, but in how the scientific community has responded to profound inexplicability by maintaining rigorous investigation rather than retreating into comfortable certainty, and how the public consciousness has embraced a cosmic enigma without demanding immediate resolution, somehow accepting that reality occasionally refuses to align with our theoretical models and our need for answers. In this way, Tabby's star has become less a problem to be solved and more a mirror reflecting humanity's evolving relationship with the unknown, reminding us that some of the most profound scientific contributions may come not from providing answers, but from teaching us to sit comfortably within the space where mystery and wonder continue to flourish. On August 15, 1977, a radio astronomer named Jerry Amon was working the night shift at Ohio State University's Big Ear Radio Telescope when he observed something that would baffle the scientific community for decades to come: a narrowband radio signal of extraordinary strength that appeared to originate from somewhere beyond our solar system, coming from the direction of the Chi Sagittarii star group. And when Amon examined the computer printout showing the signal's data, he was so startled by what he saw that he drew a red circle around the numbers and wrote the word "wow" in the margin, a reaction that would become the signal's permanent name and the defining moment of one of astronomy's greatest unsolved mysteries. The signal lasted for 72 seconds, showed characteristics consistent with an extraterrestrial origin rather than any known terrestrial interference or natural phenomenon, and possessed a strength that suggested it could only have come from an incredibly powerful transmitter located many light years away. Yet when researchers attempted to detect it again in subsequent observations, and in the years and decades that followed, the signal never reappeared, leaving behind only those few precious data points and an enduring enigma about whether humanity had briefly received a message from an intelligent civilization beyond Earth. The psychological power of the WOW signal lies in its fundamental incompleteness, the way it offers just enough evidence to suggest something profound occurred, while simultaneously remaining impossible to fully verify or explain, creating a cognitive space where rational analysis meets yearning for cosmic contact, where scientific skepticism collides with the deeply human desire to know that we are not alone in the universe. The signal exploits something fundamental in human pattern recognition, our tendency to see meaning in isolated data points and to construct narratives around incomplete information. And the fact that it appeared only once, in a way that could not be replicated or definitively ruled out as natural phenomena, transformed it into a kind of scientific Rorschach test, where different observers projected their own beliefs about extraterrestrial life onto the same ambiguous evidence. What remains remarkable decades later is how the WOW signal has maintained its grip on the public imagination, and even on serious scientific discourse, despite the complete absence of any follow-up detection, any confirmation, or any satisfactory explanation that has achieved consensus among the scientific community. And this persistence suggests that we continue to invest enormous emotional and intellectual energy into mysteries that offer us only fragmentary clues. Mysteries that may never be resolved, yet somehow seem to matter more than mysteries that have logical explanations within our current understanding of physics and astronomy. The wow signal thus stands as a monument to the limits of our knowledge and the power of uncertainty itself, reminding us that in an infinite universe, the greatest mysteries are often those that refuse to be solved, those that hover perpetually in the space between discovery and imagination, compelling us to confront the possibility that some questions may be more valuable than their answers. In the vast silence of space, astronomers have discovered something that defies our understanding of the cosmos. Brief, intensely powerful bursts of radio waves arriving at Earth from distant galaxies, lasting only milliseconds before vanishing entirely, leaving behind more questions than answers. These events, known as fast radio bursts or FRBs, were first detected in 2007 when a scientist named Duncan Lorimer noticed an unusual signal in archival data from a radio telescope, a fleeting pulse of energy so strange and so powerful that it seemed almost impossible that nature could produce such a thing. Each burst releases as much energy in a fraction of a second as our sun does in an entire day, yet we still cannot definitively explain what generates them. The mechanisms we propose strain credibility. Neutron stars colliding with black holes, magnetars experiencing catastrophic starquakes, exotic particles from dimensions beyond our own, or perhaps technology so advanced that civilizations we have yet to encounter are deliberately broadcasting signals across the galaxy for reasons we cannot fathom. What makes this phenomenon particularly unsettling is that approximately one-third of known fast radio bursts repeat, appearing to originate from the same location multiple times, suggesting something that can survive the burst and produce additional emissions. Yet many others appear only once and never again, as if the universe is deliberately withholding the rules of their occurrence from us. Scientists continue analyzing these signals with increasing precision, yet each new discovery seems to contradict previous assumptions, creating a situation where the phenomena become stranger and more inexplicable the more closely we examine them. We have constructed elaborate theories, built sophisticated detection networks, and dedicated enormous resources to solving the mystery, yet the universe refuses to surrender its secret, leaving us suspended in a state of profound ignorance despite possessing the most advanced observational technology ever created. Perhaps this is the universe's way of reminding us that no matter how far our telescopes reach or how sensitive our instruments become, there exist phenomena so fundamentally alien to our experience that they may forever resist explanation, standing as monuments to the vast gulf between what we know and what remains unknowable. In 2020, researchers detected an FRB originating from within our own Milky Way galaxy, a discovery that simultaneously brought the mystery closer to home and suggested that the mechanisms producing these bursts might operate far more universally than previously imagined, occurring not only in the distant reaches of the universe, but potentially anywhere stellar catastrophe finds the conditions to unfold. Yet even this galactic FRB, detected from the magnetar SGR 1935 plus 2154, provided only tantalizing glimpses rather than definitive answers. A single, brilliant flash that illuminated the darkness for merely a fraction of a second before reminding us once again that the universe guards its deepest secrets behind a veil of transient, inexplicable signals. Consider the sheer scale of the universe for a moment, a cosmos so incomprehensibly vast that it contains an estimated 2 trillion galaxies, each harboring billions or trillions of stars, and around many of those stars orbit planets that could theoretically support life as we understand it. Given these astronomical numbers, the probability that Earth represents the only place in existence where conscious beings evolved seems not merely unlikely but statistically absurd. Yet when we look up at the night sky with our most powerful telescopes and direct our most sensitive listening devices toward the heavens in search of any signal, any transmission, any whisper of intelligent civilization out there, we encounter only silence. An overwhelming and profound emptiness that has puzzled scientists and philosophers for decades. This contradiction between what the mathematics of probability almost demands should exist and what we actually observe in the universe is known as the Fermi Paradox, named after physicist Enrico Fermi, who famously asked during lunch in 1950, if intelligent life is so common, where is everybody? The mechanism behind this paradox operates on a deceptively simple logical foundation. The Drake equation attempts to estimate the number of communicative civilizations in our galaxy by multiplying together factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, and the fraction of those that develop intelligence and technology. Even when researchers use conservative estimates for these variables, the resulting numbers suggest that countless advanced civilizations should exist within our galaxy alone. Yet humanity's decades of radio astronomy, from Project Ozma in 1960 through the Breakthrough Listen initiative today, have detected nothing conclusive: no television broadcasts, no mathematical sequences, no obvious beacon calling out across the darkness. What makes this paradox persist in our consciousness, despite its seemingly simple resolution, is that none of the proposed explanations feels entirely satisfying or complete. Perhaps civilizations destroy themselves through warfare or environmental collapse before achieving the technological capability for interstellar communication, a grim possibility that haunts our thinking about our own future. Perhaps intelligent life is far rarer than our equations suggest, with some crucial variable in the Drake equation being vanishingly small. Perhaps civilizations do exist but choose deliberately not to communicate, adhering to what science fiction writers call the prime directive, a cosmic law of non-interference. Perhaps the distances are so incomprehensibly vast, and the timescales so enormously long, that civilizations rise and fall without ever overlapping in time or space enough to make contact. Or perhaps, most unsettling of all, we are asking the wrong questions entirely, searching for signals in frequencies and formats that an alien intelligence would never think to use, as though a human calling into the ocean might never realize that whales are answering back in ways our ears cannot perceive. Consider the question that haunts astronomy and cosmology. If the universe contains billions of galaxies, each containing billions of stars, and if even a tiny fraction of those stars possess planets capable of supporting life, then where is everybody? This paradox, formerly known as the Fermi Paradox, has led scientists and philosophers to propose what may be the most unsettling explanation ever conceived: the Great Filter. The concept operates on a deceptively simple principle. Somewhere between the emergence of life itself and the development of spacefaring civilizations, there exists an evolutionary or technological barrier so formidable, so improbable, or so deadly that it prevents almost all life from progressing beyond it. This filter could exist in our past, meaning we have somehow miraculously survived it, or it could exist in our future, meaning all the civilizations we might detect have already perished before reaching detectability. The mechanism underlying this theory rests on probability mathematics applied to biological and technological development. If we assume that the universe should be teeming with advanced civilizations capable of interstellar communication or travel, yet observe only profound silence, then one of our assumptions must be catastrophically wrong. Either the origin of life itself is far rarer than we believed, or the jump from simple organisms to intelligent beings is vastly more improbable, or the transition from intelligence to technological maturity is nearly impossible, or civilizations inevitably destroy themselves shortly after achieving the capacity to do so. What makes the Great Filter genuinely disturbing is not merely its logical coherence, but our inability to determine which scenario applies to us. If the filter lies behind us in our evolutionary past, then we are extraordinarily fortunate survivors of an almost inconceivable improbability, which should humble us profoundly. If the filter lies ahead in our future, then every spacefaring civilization that might theoretically detect us has already experienced extinction, suggesting that technological advancement itself carries an intrinsic death sentence. We continue our ordinary lives, pursuing ordinary concerns, while allowing this possibility to exist in the background of human knowledge, neither fully confronting it nor abandoning it, as if civilization itself is a temporary phenomenon that persists only because we lack sufficient perspective to truly understand the odds arrayed against us. Perhaps this is why we build telescopes and listen to the stars with such desperate hope, searching for any signal that might confirm we are not alone. Or perhaps we are searching for reassurance that our silence, our isolation, is not a harbinger of what inevitably awaits us. Yet in this very act of listening, we perform an inadvertent test of our own survival. The longer we persist in transmitting signals into the void without encountering a response, the more credible becomes the darkest interpretation of the Great Filter, not as a barrier we have passed, but as a deadline we are approaching. The history of human civilization offers a grim case study. We have developed the technological capacity for self-annihilation only within the last 80 years, and we have come perilously close to exercising it more than once. Consider the sheer improbability of your existence in this particular universe at this particular moment in cosmic history, surrounded by physical constants that seem almost impossibly fine-tuned to permit the emergence of conscious observers like yourself. A coincidence so profound that it has led philosophers and physicists to propose that perhaps the universe itself is fundamentally shaped by the requirement that observers must exist within it. The Anthropic Principle comes in multiple forms, from the weak version, which simply states that we should not be surprised to find ourselves in a universe compatible with our existence, to the strong version, which suggests that the universe must have properties that allow consciousness to develop within it at some stage, and even to the participatory version proposed by physicist John Wheeler, which argues that observers are not merely passive witnesses to reality, but active participants, whose very act of observation retroactively brings the universe into existence. What makes this principle so deeply unsettling is that it appears to invert our understanding of causality itself, suggesting that rather than the universe creating the conditions for observers, observers in some sense call the universe into being, or at minimum, that the existence of conscious beings is not an accidental byproduct of physical laws, but rather a fundamental requirement that those laws must satisfy. The mechanism underlying this conceptual framework relies on a strange loop of reasoning. We find ourselves in a universe with precisely the right constants for life to exist, and we explain this apparent miracle not through invoking design or chance, but by proposing that of course we find ourselves in such a universe. Because in any universe lacking these properties, there would be no one present to observe it and wonder about the improbability. Yet this explanation, while logically sound, carries implications so disturbing that most people never fully contemplate them, for it suggests that consciousness might not be an emergent property of matter, but rather a fundamental aspect of reality itself, woven into the fabric of existence. We have become comfortable with this principle because it allows us to avoid both the trap of assuming we are cosmically special and the trap of assuming we are merely accidents, instead positioning ourselves in a middle ground of circular self-justification that feels intellectually safe even as it challenges the very foundations of materialism and determinism. Yet when we peer deeper into this comfortable middle ground, we discover that it dissolves into troubling questions. If consciousness is fundamental rather than emergent, what does that mean for the nature of mind itself, and why should we trust our observations of a universe that may exist only because we are here to perceive it? Perhaps the most unsettling implication is that we cannot step outside this loop to verify it. Any universe we could possibly observe or measure is by definition one in which observers exist to do the observing, leaving us forever trapped within a logical circle that we cannot escape, only endlessly examine from within, unable to determine whether we have discovered a profound truth about reality or merely constructed an elaborate philosophical tautology. The universe operates according to fundamental constants, numbers so precise and delicately calibrated that even the slightest variation would render complex chemistry, stars, planets, and life itself impossible to form. The gravitational constant, the strength of electromagnetic force, the mass ratios of particles, the expansion rate of space itself, each of these values appears exquisitely fine-tuned to permit the existence of observers like us. A phenomenon so statistically improbable that physicists struggle to explain it without invoking either multiverse theory or design. Consider the strength of the strong nuclear force. If it were merely 2% stronger, protons would fuse so readily that no hydrogen would survive the Big Bang, eliminating water and stellar nucleosynthesis. If it were slightly weaker, deuterium would never form, again preventing star formation and the creation of heavier elements necessary for chemistry. The weak nuclear force governs radioactive decay and must fall within a narrow band to allow the universe to cool properly after the Big Bang while still permitting the nuclear reactions that power stars. The fine structure constant, which determines electromagnetic interaction strength, must sit at approximately 1 divided by 137, a number so peculiar that physicists have spent decades searching for deeper mathematical explanations, yet none have surfaced. The cosmological constant, which drives cosmic acceleration, appears balanced on a knife's edge between values that would either collapse the universe immediately or expand it so rapidly that galaxies could never form. Our brains recognize these coincidences as extraordinary, yet we have normalized this reality through the application of selection bias reasoning. The Anthropic Principle suggests that we observe a fine-tuned universe simply because observers could only exist in fine-tuned universes, making the observation logically inevitable rather than genuinely remarkable. We persist in accepting this explanation despite its philosophical circularity, treating mathematical improbability as philosophically resolved through tautology rather than demanding genuine understanding of why physical law itself takes this particular form. Yet the multiverse hypothesis, while mathematically elegant, merely displaces the question rather than answering it. If infinite universes exist with varying constants, what explains the laws that govern their generation, and why should those meta-laws themselves permit life-permitting variation rather than forbidding it entirely? The deeper discomfort lies in recognizing that fine-tuning arguments ultimately confront us with a choice between accepting mystery, that the constants simply are what they are, or invoking explanations that merely recede the mystery further into unobservable realms, leaving us no closer to genuine understanding of existence itself. Perhaps the most honest acknowledgement is that fine-tuning reveals the limits of scientific explanation itself, that physics can describe how the universe operates within its constants, but may be fundamentally incapable of explaining why those constants possess their particular values, suggesting that some questions about existence lie beyond the methodological reach of empirical inquiry. In the 1970s, NASA launched two spacecraft called Pioneer 10 and Pioneer 11 on humanity's first missions to the outer solar system, and these vessels were designed to travel beyond the planets and eventually escape the gravitational pull of the Sun entirely, carrying golden records with sounds and images from Earth into the cosmic void. For decades, these spacecraft performed their duties with remarkable precision, transmitting data back across the vast distances of space as they journeyed deeper into regions no human technology had previously explored. However, as scientists carefully tracked the trajectories of both Pioneer probes throughout the 1980s and 90s, they began noticing something extraordinary and deeply troubling. The spacecraft were slowing down slightly more than the physics equations predicted they should, as if some invisible hand were gently pulling them backward toward the Sun with a consistent and measurable force. The acceleration was minuscule, roughly the equivalent of a mosquito landing on a car, yet it was absolutely real, confirmed by multiple independent observations and calculations that left physicists scrambling to explain what could possibly account for this mysterious deceleration. Scientists proposed countless explanations ranging from solar wind pressure to asymmetrical heat radiation from the probes themselves, to undiscovered asteroids and gravitational influences from unknown objects in the outer solar system. Yet none of these theories fully explained the observed phenomenon in a way that satisfied the mathematical requirements of classical physics. The Pioneer Anomaly persisted as one of modern astronomy's most confounding mysteries for nearly 40 years, prompting serious scientific debate about whether the laws of physics themselves might require fundamental revision, or whether humanity's instruments were somehow systematically flawed in ways nobody had yet conceived. What makes this phenomenon psychologically fascinating is how the scientific community normalized the existence of an unexplained deviation from physical law that nobody could definitively solve, treating it as an acceptable mystery rather than a fundamental challenge to understanding. Yet the more recent analyses suggest that much of the anomaly may have resulted from thermal radiation effects that were simply underestimated. Meaning the universe perhaps did not break after all, but rather reflected the limitations of our initial measurements and assumptions about how energy dissipates from aging spacecraft traveling through the cold silence of space. This resolution itself became a lesson in scientific humility, reminding us that the most profound mysteries sometimes yield not to revolutionary new physics, but to painstaking recalibration of our instruments and a deeper appreciation for the subtle ways energy behaves in environments we have barely begun to understand. The Pioneer probes themselves, now decades beyond their original mission parameters and still transmitting faint signals from the edge of interstellar space, stand as monuments to this humbling principle, silent witnesses to humanity's endless cycle of questioning, theorizing, and gradually refining our grasp of a cosmos far more intricate than our first equations could capture. When spacecraft pass by planets at high speeds, physicists expect them to behave according to well-established laws of gravity and orbital mechanics. Yet a strange pattern has emerged in the data that challenges this fundamental assumption about how the universe works. Between 1998 and 2010, multiple spacecraft including NEAR Shoemaker, Cassini, Messenger, and Rosetta experienced unexplained variations in their velocities as they flew past Earth, Mars, and Jupiter, with some gaining speed and others losing it in ways that violated every calculation made beforehand. The anomalies were small, typically measured in millimeters per second, but in the precise realm of space exploration, where missions depend on accurate trajectory predictions down to the centimeter, these deviations represented a genuine mystery that nobody could adequately explain. Physicists analyzed the gravitational influences of the planets, the relativistic effects predicted by Einstein, the solar wind, and countless other factors, yet the measurements still refused to align with theory in a consistent and predictable manner. The psychological mechanism at work here involves what might be called the confidence trap in scientific consensus, wherein a community of experts becomes so convinced that a particular framework is correct that anomalous data is initially dismissed as measurement error, instrument malfunction, or statistical noise rather than as evidence of genuine physical phenomena worthy of serious investigation. This defensive stance makes intuitive sense because accepting that fundamental orbital mechanics might be incomplete would require rebuilding decades of theoretical work and potentially invalidating countless mission calculations, creating enormous practical and philosophical consequences that institutions understandably resist. The scientific establishment unconsciously normalized these discrepancies by simply accepting them as minor calibration quirks and moving forward with missions while privately acknowledging that something remained unexplained but unresolved. What persists is a peculiar situation where space agencies continue to launch sophisticated equipment that behaves in ways partially at odds with our most fundamental understanding of gravity and planetary dynamics. Yet this fact generates remarkably little public discussion or urgent theoretical research dedicated to resolving the contradiction, suggesting that we have collectively agreed to tolerate a permanent crack in our understanding of physics as long as it remains small enough not to interfere with practical engineering goals. Perhaps the most revealing aspect of this situation is that the Flyby anomaly remains unsolved not because it lacks scientific importance, but because its resolution would require admitting that our confidence in gravitational theory may have been premature, a conclusion far more destabilizing to institutional credibility than simply leaving the mystery in an indefinite state of quiet acknowledgement. When the universe began, in that first infinitesimal fraction of a second after the Big Bang, something extraordinary and deeply troubling occurred that physicists still cannot adequately explain. According to our best understanding of the fundamental laws of physics, matter and antimatter should have been created in absolutely equal quantities, perfectly balanced as mirror images of one another, and when these two opposing forms of substance encountered each other, they should have annihilated in a brilliant flash of pure energy, leaving behind nothing but radiation and light. If this theoretically predicted outcome had actually come to pass, if the universe had followed the logical mathematical symmetry that our equations suggested it must follow, then there would be no stars, no planets, no galaxies, and crucially, no life of any kind, because everything would have canceled out completely into oblivion. Yet here we are, existing in a cosmos made almost entirely of matter, with antimatter relegated to such rarity that we barely encounter it, except in our most powerful particle accelerators and in certain cosmic phenomena. This asymmetry, this inexplicable preference for matter over antimatter, represents one of the deepest mysteries in physics, and physicists refer to it as the matter-antimatter asymmetry problem, a phenomenon that directly contradicts our most carefully constructed theories about how reality should fundamentally operate at its deepest level. The mechanisms proposed to explain this cosmic imbalance include variations in how matter and antimatter decay, subtle differences in their interactions with fundamental forces, or exotic processes occurring in those earliest moments after creation that we simply cannot replicate or fully understand. We have constructed increasingly elaborate theoretical frameworks and conducted increasingly sophisticated experiments attempting to identify where and how this symmetry breaking occurred. Yet the central mystery persists despite decades of intense investigation. What makes this particularly strange is how completely we have normalized this profound puzzle, how we proceed with our scientific understanding while accepting that the very existence of observable reality violates the symmetrical laws we believe govern it, creating a fundamental disconnect between what our equations predict and what we actually observe in the universe around us. This gap between prediction and reality forces us to confront an uncomfortable possibility: that our fundamental understanding of symmetry itself may be incomplete, that nature operates according to principles we have yet to discover, or that the universe's preference for matter represents not a flaw in creation, but a hidden organizing principle waiting to be decoded by future generations of physicists willing to question assumptions we have long taken for granted. Until we solve this riddle, we remain fundamentally ignorant of why anything exists at all, why the universe bothered to create a stage upon which consciousness could eventually emerge to contemplate its own improbable existence, making antimatter asymmetry not merely a technical problem for particle physicists to resolve, but perhaps the most essential question any thinking being can ask. We live in an age of renewable energy and technological progress, yet we have built our entire vision of a sustainable future on a resource that may be even more destructive to extract than the fossil fuels we are trying to replace, and almost nobody talks about it. Lithium mining has become the backbone of the green energy revolution, essential for batteries in electric vehicles, solar storage systems, and the smartphones and laptops that define modern life. But the environmental and human cost of obtaining this lightweight metal reveals a fundamental contradiction in how we approach solving planetary crises. The largest lithium reserves exist in South America's Lithium Triangle, spanning parts of Argentina, Bolivia, and Chile, where mining operations have drained aquifers that indigenous communities have relied upon for thousands of years, transforming fertile land into barren salt flats and contaminating water supplies with toxic chemicals used in the extraction process. 1 ton of lithium requires approximately 500,000 gallons of water to extract, and in regions already experiencing severe drought, this demand has created situations where farmers watch their crops wither while mining companies drain the groundwater beneath their fields. Yet the expansion of these operations continues accelerating because the world's demand for batteries grows exponentially each year. What makes this particularly troubling is the psychological mechanism at work. We have successfully convinced ourselves that the environmental damage caused by lithium mining is acceptable because it serves the greater good of fighting climate change, creating a moral hierarchy where one form of environmental destruction is justified by preventing another, and we never fully reckon with the fact that we are simply shifting the burden of our consumption patterns onto some of the most vulnerable populations on Earth. The mining companies, the governments that profit from mining permits, and the consumers who purchase devices powered by lithium batteries all participate in a system that abstracts away the human suffering involved, making it invisible through geographic distance and complex supply chains, so that when someone charges their electric car or uses their smartphone, they feel virtuous about their environmental consciousness while remaining completely disconnected from the communities whose water sources are being poisoned for their benefit. We have normalized this arrangement because addressing it would require fundamentally reconsidering our approach to technology, consumption, and the false solutions we have embraced, and that kind of systemic change feels impossibly difficult compared to simply buying an electric vehicle and feeling like we have solved the problem. The uncomfortable truth is that we have created a system where the solution to one injustice simply manufactures another, and until we are willing to confront the uncomfortable reality that sustainable consumption is largely a myth, that true sustainability would require dramatically reducing our consumption rather than simply swapping one extractive industry for another, we will continue to sacrifice the lands and lives of distant others on the altar of our technological progress. When astronomers began measuring the rotational speeds of galaxies in the 1970s, they encountered a profound discrepancy that has never been adequately resolved, a gap between what physics predicts and what the universe actually displays. According to the laws of gravity and orbital mechanics established by Newton and refined by Einstein, stars orbiting at the outer edges of spiral galaxies should move more slowly than those closer to the center, much like planets in our solar system, where Mercury moves faster than Neptune. Yet observational data consistently shows something radically different. Stars at the periphery of galaxies move at nearly the same velocity as those deeper within the galactic disk, defying every expectation derived from gravitational theory. This observation suggests that either the visible matter we can detect through telescopes and radiation represents only a fraction of the galaxy's actual mass, or our fundamental understanding of gravity itself requires radical revision at cosmic scales. The astronomical community responded by proposing the existence of dark matter, an invisible substance that comprises roughly 85% of all matter in the universe, yet cannot be directly observed or measured through any conventional means. This explanation became the dominant framework within mainstream cosmology, allowing scientists to maintain the existing gravitational models while attributing the anomaly to undetected material rather than questioning the theory itself. What persists as remarkable is how thoroughly this invisible solution has been accepted and normalized within scientific discourse, how dark matter has become as commonplace in astrophysical conversation as ordinary matter, despite the fact that it has never been directly detected or confirmed to exist. The psychological mechanism at work here involves the human tendency to extend existing frameworks rather than abandon them, to add complexity to a theory rather than question its foundations, and the institutional momentum that develops once a particular explanation becomes the dominant paradigm. Decades have passed since these rotational anomalies were first documented. Billions of dollars have been spent searching for dark matter particles in underground laboratories, yet not a single dark matter particle has been conclusively identified. The galaxy rotation problem remains one of the deepest unsolved mysteries in physics, yet it is rarely presented to the public with the urgency or existential weight that such a fundamental gap in understanding should carry. Instead, it has become absorbed into the background of accepted cosmological knowledge, normalized and filed away as a problem with a solution, even though that solution remains entirely hypothetical and unproven. Alternative theories such as modified Newtonian dynamics, MOND, have been proposed as potential explanations that would preserve our understanding of gravity while accounting for observed galactic behavior. Yet these frameworks remain marginalized within the mainstream scientific establishment, suggesting that institutional investment in dark matter may be as much a sociological phenomenon as a scientific one. The rotation curves of galaxies thus stand as a reminder that the most profound mysteries often hide in plain sight, concealed beneath layers of accepted explanation that themselves demand scrutiny. Consider the remarkable phenomenon of bird migration, where billions of creatures navigate across continents with a precision that defies conventional explanation, traveling thousands of miles to locations they have never visited before, following invisible pathways that span the entire globe with an accuracy measured in mere meters rather than miles. And it turns out that at the very foundation of this extraordinary navigation lies something that should not exist according to the rules we thought governed biology: quantum mechanics operating inside the warm, wet, chaotic environment of living cells. Scientists have discovered that certain birds, particularly European robins, possess a protein in their eyes called cryptochrome that operates through a process called quantum entanglement, where particles become mysteriously connected across distances such that the state of one instantly influences the state of another, defying any reasonable biological explanation for how such a delicate quantum state could possibly survive the electromagnetic noise and thermal chaos of a living organism. The mechanism appears to work through radical pairs, which are molecules containing unpaired electrons that become entangled in a way that allows the bird's brain to detect the Earth's magnetic field with supernatural precision, converting quantum information into neural signals that somehow translate into directional awareness, creating a biological compass that exists at the intersection between the quantum realm and conscious perception. Yet this violation of what we assumed biology could accomplish persists not as some exotic laboratory anomaly, but as an integral feature of how billions of creatures navigate the planet every single year, operating invisibly in the bodies of animals we see constantly, and despite decades of accumulating evidence that quantum processes are not merely theoretical curiosities, but functional components of living systems. Most discussions of biology continue to operate as though the quantum realm and biological systems exist in completely separate domains, allowing this cognitive dissonance to persist in our collective understanding of how life actually functions at its most fundamental levels. This compartmentalization of knowledge reflects a deeper scientific conservatism, where quantum biology remains confined to specialized journals, while introductory biology textbooks present life as a purely classical system. Despite mounting evidence that photosynthesis, enzyme catalysis, and olfaction may all depend on quantum tunneling and coherence, effects operating at biological scales. The implications are profound. If quantum mechanics is not incidental to biology but central to it, then our understanding of life itself requires fundamental revision, suggesting that consciousness, navigation, and perhaps even the origins of life itself may be phenomena that cannot be fully explained without accounting for the quantum nature of the molecular systems from which they emerge. This reframing transforms birds from mere biological automata into quantum processors, suggesting that the subjective experience of navigation, the felt sense of direction that guides a migrating warbler across an ocean, may emerge from the collapse of quantum superposition states in the cryptochrome molecules of its retina, making consciousness itself a quantum phenomenon woven into the fabric of avian perception. Plants have been performing one of the most efficient energy conversion processes on Earth for billions of years. Yet only in the last 2 decades have scientists discovered something that fundamentally challenges our understanding of how this process actually works at the molecular level. When photosynthesis occurs, light energy strikes the chlorophyll molecules in plant cells, and this energy must somehow find its way through a maze of proteins and molecular structures to reach the reaction center, where it can be converted into chemical energy. Classical physics would suggest that this energy would take a relatively random, meandering path through the photosynthetic apparatus, bouncing around inefficiently like a pinball machine, losing energy to heat at every collision. Yet experimental evidence has shown that photosynthesis achieves nearly perfect efficiency, around 95% or higher in many cases, which should be physically impossible if energy transport relied on classical random diffusion. What researchers discovered through spectroscopic techniques and quantum measurements is that the energy appears to exist in a state of quantum coherence, meaning it simultaneously explores multiple pathways through the molecular structure at once, as if the quantum energy is traveling down every possible route in parallel until reaching the reaction center with remarkable precision. This quantum behavior persists at warm, wet biological temperatures inside living plant cells, conditions where quantum effects are typically destroyed almost instantly by environmental interference, a phenomenon called decoherence. The mechanism that allows this coherence to persist remains only partially understood, though researchers have proposed that the protein scaffolding around the photosynthetic complexes may actively protect quantum states, or that the vibrational modes of molecules might somehow regenerate coherence as quickly as it decays. What is particularly unsettling about this phenomenon is how plants achieved quantum-level optimization through evolution without any apparent understanding of quantum mechanics, suggesting that nature routinely solves problems at the quantum scale that human engineers struggle to maintain even in laboratory conditions with extreme isolation and cooling. We have normalized this discovery into our scientific literature, accepted it into textbooks, and continued growing plants without pause, yet the underlying question remains largely unexamined in popular consciousness. If evolution could refine quantum processes to near-perfect efficiency inside a leaf, what other quantum phenomena might be operating throughout biology that we have simply failed to notice because we assumed they were impossible? Recent studies have suggested quantum coherence might similarly enhance efficiency in avian navigation, enzyme catalysis, and even olfaction, hinting that quantum biology may be far more widespread than photosynthesis alone, operating as a hidden layer of optimization throughout living systems that we are only beginning to perceive. Among the most resilient organisms ever discovered on Earth exists a microscopic creature called the tardigrade, also known as a water bear, which has demonstrated an almost impossible ability to survive the extreme conditions of outer space itself. In the year 2007, scientists launched tardigrades aboard a Russian Foton spacecraft to test whether these tiny animals could withstand the vacuum of space, intense radiation, extreme temperature fluctuations, and cosmic rays. And to nearly universal astonishment, approximately 68% of the specimens returned alive and unharmed after 10 days of exposure to the unforgiving environment of low Earth orbit. The tardigrade, which typically measures only half a millimeter in length, possesses an extraordinary biological mechanism called cryptobiosis, a state of metabolic suspension in which the organism can reduce its water content to nearly 0%, essentially entering a dormant condition where it requires virtually no oxygen, no food, and no water to survive for extended periods. When environmental conditions become hostile, the tardigrade systematically removes water from its cells and compresses its body into a hardened state known as a ton, which protects its internal structures from radiation damage, dehydration, and the crushing pressures of vacuum while simultaneously allowing its DNA to remain stable and protected. The creature's cellular architecture contains specialized proteins and organic compounds that repair DNA damage more efficiently than almost any other known organism, and it produces sugars such as trehalose that stabilize cell membranes and proteins against radiation and freezing, creating a biological shield against conditions that would obliterate virtually every other form of life. Despite possessing a nervous system and functioning organs, the tardigrade can suspend these processes almost entirely, achieving a state of biological stasis that challenges our fundamental understanding of what life requires to persist. We have now normalized the existence of these creatures as merely another peculiar aspect of nature, accepting their survival capabilities with scientific curiosity rather than the profound astonishment such resilience should inspire. And yet the tardigrade's ability to traverse the void between worlds, to endure cosmic radiation that would shred human tissue, and to emerge from absolute zero temperatures completely unscathed suggests something deeply unusual about the boundaries between life and non-life, between possible and impossible. Perhaps the tardigrade's existence reminds us that life itself is far more tenacious and adaptable than we dare imagine, and that the mechanisms of survival, when stripped to their most fundamental biological essence, operate according to principles we have yet to fully comprehend, suggesting that similar microscopic pioneers may already inhabit the harsh environments of distant worlds, waiting only for our discovery. The discovery of tardigrades in Earth's most extreme environments, from the frozen peaks of the Himalayas to the boiling hot springs of geothermal vents, suggests that life's capacity for adaptation may be far more universal than our carbon-based models of biology have previously allowed us to conceive, opening profound questions about what forms consciousness and survival might take on worlds we have yet to explore. Consider a patient suffering from chronic pain who enters a clinical trial and receives a pill that contains nothing but sugar and binding agents, yet within hours reports genuine relief from their symptoms, their body responding as though actual medication had been administered, their brain somehow convincing their nervous system that healing is occurring when objectively no pharmaceutical intervention has taken place. This is the placebo effect, and it represents one of the most profound paradoxes in modern medicine because it demonstrates conclusively that our expectations and beliefs can trigger measurable, physiological changes in our bodies that should not be possible according to conventional biology. The mechanism underlying this phenomenon operates through several interconnected pathways within the nervous system. When a person believes they have received treatment, their brain releases endogenous chemicals including endorphins and dopamine, neurotransmitters that genuinely reduce pain perception and improve mood, meaning the body is literally manufacturing its own medication in response to belief alone. Additionally, the expectation of improvement activates the prefrontal cortex in ways that suppress the anterior insula, the brain region responsible for processing pain signals, effectively reducing the actual neurological sensation before it reaches consciousness. The ritual and context surrounding treatment amplifies these effects, which is why a placebo works better when administered by a trusted doctor in an official medical setting than when administered anonymously, because the entire theatrical environment of medicine becomes part of the cure itself. What makes this genuinely unsettling is that the placebo effect works even when the patient knows they are receiving a placebo, suggesting that the conscious mind's logical understanding of reality has remarkably little control over what the body actually experiences. We have normalized this phenomenon by integrating it into medical research protocols and acknowledging its power in healthcare, yet we still cannot fully explain how mere expectation can override objective biological reality, how the immaterial realm of thought and belief can reach down into cells and tissues and command them to behave differently, challenging the fundamental assumption that consciousness and body operate in separate domains. Perhaps the most humbling aspect is that this mind-body bridge works not through deception, but through the activation of genuine healing mechanisms that exist within us all along, waiting only for the signal of belief to be engaged, suggesting that the boundary between what we call real medicine and mere psychology may be far more permeable than our categories allow. This realization invites us to reconsider not just medicine, but the nature of human potential itself. If belief can heal pain, what other capabilities might lie dormant within us, waiting only for the conviction that they are possible to be awakened into being? The history of medicine itself becomes reinterpreted through this lens. Countless treatments once considered miraculous cures may have derived their efficacy not from their chemical composition, but from the concentrated belief systems surrounding them, suggesting that our ancestors were not foolish, but were accessing real therapeutic mechanisms through different means than we now employ. If the placebo effect represents the remarkable power of positive expectation to heal the body, then the nocebo effect represents its dark mirror, a phenomenon where the mere belief that something will harm you actually causes it to harm you. And the strange truth is that this effect is just as real, just as measurable, and perhaps even more powerful than its optimistic counterpart. Consider the documented cases of patients who were told they had a terminal illness, only for doctors to later discover that the diagnosis was entirely mistaken. Yet by that point the patient had already begun their physiological decline, their body deteriorating in ways consistent with the illness they believed they had rather than the one they actually possessed, suggesting that the mind's conviction about impending harm can literally reprogram the body's biochemistry and immune response. The mechanism operates through a complex interplay of neurological pathways and stress hormones, where the expectation of negative outcomes triggers the release of cortisol and adrenaline, suppresses immune function, increases inflammation, and alters pain perception through the release of cholecystokinin rather than endogenous opioids, essentially creating a self-fulfilling prophecy at the physiological level where belief becomes indistinguishable from reality. Medical professionals have observed nocebo effects so pronounced that patients given placebo pills while being told they were painkillers actually experienced increased pain, and individuals informed about the side effects of medications sometimes develop those exact side effects even when receiving inert substances, demonstrating that the power of expectation can override the actual chemical composition of what enters the body. What makes this phenomenon particularly unsettling is how thoroughly we have normalized it within modern medical practice, where informed consent requires telling patients about potential side effects, yet that very act of disclosure inadvertently increases the likelihood that those side effects will manifest, creating an impossible paradox where being honest about risks actually increases those risks through the nocebo mechanism itself. And doctors find themselves trapped between ethical obligations and the unintended consequences of transparency. Some researchers have begun exploring whether this dilemma might be resolved through the strategic framing of information, presenting risks in terms of resilience and recovery rather than harm and decline, though the question of whether such reframing constitutes ethical disclosure or merely a more sophisticated form of manipulation remains genuinely unresolved. The nocebo effect thus reveals an uncomfortable truth about the relationship between knowledge and agency, that sometimes knowing about a potential harm creates the very conditions for it to manifest, suggesting that perfect information and perfect health may not always be compatible goals, and that the most conscientious medical practice may require not just transparency but wisdom about how and when certain truths should be communicated. Consider the moment when you think of an old friend you haven't spoken to in years, and within hours that person calls you, or you unexpectedly see their name appear 3 times in completely unrelated contexts, or you both arrive at the same obscure location neither planned to visit. These moments feel extraordinary, laden with meaning, as if the universe itself has conspired to connect you across time and space. Most people experience synchronicity events regularly enough that they become part of the ordinary texture of life, yet each occurrence carries a peculiar weight that demands explanation. The timing feels too precise to dismiss as mere coincidence, the probability too improbable to attribute to random chance, and the emotional resonance too powerful to ignore as meaningless noise in the fabric of daily existence. We notice these patterns intensely, we remember them vividly, and we often interpret them as evidence that something deeper governs reality than mechanical cause and effect. Yet the mechanism behind this phenomenon has nothing to do with cosmic alignment or hidden forces operating beneath the surface of the world. What actually occurs is a combination of pattern recognition, confirmation bias, and selective memory that causes our brains to amplify certain connections while filtering out the overwhelming majority of non-connections that occur constantly around us. Our minds are essentially prediction machines that evolved to detect patterns in the environment because organisms that could recognize patterns survived longer than those that could not. This tendency remains so powerful that we detect patterns even where none objectively exist, a phenomenon researchers call apophenia, and we simultaneously forget the thousands of times we thought of someone and they never called, or the countless moments when synchronistic feeling events did not occur. We live among an infinite sea of data points, and our attention naturally gravitates toward the ones that feel significant while rendering invisible the vastly larger set that contradicts our sense of cosmic order. The persistence of synchronicity belief, despite complete understanding of these cognitive mechanisms, suggests that the human mind prioritizes meaningful narrative over accurate statistical assessment, and that the emotional satisfaction derived from perceiving cosmic significance in random events outweighs our commitment to rational analysis. We have normalized this broken perception so thoroughly that we rarely pause to acknowledge how fundamentally we distort probability through the lens of subjective experience. Yet this distortion may itself serve a purpose. The narrative coherence we impose on random events, however statistically unfounded, provides psychological stability and a sense of agency in a fundamentally indifferent universe, suggesting that our cognitive errors are not bugs but features that make existence bearable. Perhaps this explains why we remain so invested in synchronicity despite knowing better. The illusion of meaningful connection, however cognitively constructed, offers more sustenance than the truth that we are isolated agents navigating an uncaring cosmos, and so we choose the comforting story our minds naturally tell us. You walk into a coffee shop you have never visited before, and as the barista hands you your order, a conversation between two strangers at the next table reaches your ears. And suddenly, inexplicably, you feel as though you have lived this exact moment previously, down to the specific inflection of their voices and the precise angle of afternoon light streaming through the window. Yet you know with absolute certainty that this is impossible because you have never been here before, and this sensation, this strange temporal echo, strikes you with an intensity that momentarily disrupts your sense of linear time and leaves you questioning whether memory itself might be fundamentally unreliable. This phenomenon, known as déjà vu, from the French phrase meaning already seen, affects approximately 60 to 70% of people at least once in their lifetime, and it represents one of the most peculiar malfunctions of human consciousness, a glitch in the machinery of perception that challenges our basic understanding of how memory and recognition actually function. The leading neurological explanations suggest that déjà vu occurs when there is a brief disconnection between the brain's recognition systems and its memory encoding systems, wherein the present moment triggers a sense of familiarity through pattern matching with past experiences, yet the specific memory itself fails to surface into conscious awareness, leaving only the ghost of recognition without the substance of recollection, as if your brain recognizes the melody but cannot recall the song. Some neuroscientists propose that déjà vu emerges from a momentary hologram effect, where similar visual elements or emotional textures from different memories momentarily overlap, creating an illusion of repetition where none exists, while others suggest it stems from a timing glitch in how the brain processes current sensory information alongside memory retrieval, causing the present to feel retroactively familiar even as you experience it. Yet despite decades of research and increasingly sophisticated neuroimaging technology, we have arrived at no definitive explanation for why this occurs, and we continue to experience déjà vu with regularity, accepting it as simply another quirk of consciousness rather than the profound anomaly it truly represents. As though the human mind's ability to convince itself that it has lived through something it demonstrably has not is merely a minor computational error, rather than evidence that our fundamental sense of temporal sequence and personal history might be far more constructed and malleable than we typically acknowledge. Perhaps this is why déjà vu unsettles us so profoundly, not because it is rare or inexplicable, but because it offers a glimpse into the uncomfortable truth that consciousness itself may be less a reliable chronicle of lived experience and more a continuous act of creative reconstruction, where the boundary between what we have truly experienced and what our minds convince us we have experienced remains perpetually blurred. Imagine if several centuries of human history simply never happened, that vast stretches of documented time were fabricated wholesale, inserted into our timeline to serve political or religious agendas, and that the world we know today is actually several hundred years younger than we believe. This is the premise of the phantom time hypothesis, a fringe historical theory proposing that approximately 300 years were added to our calendar between the years 800 and 1100, particularly during the period known as the early Middle Ages. The hypothesis suggests that this monumental deception was orchestrated by the Holy Roman Emperor Otto III, working in collusion with Pope Sylvester II and other ecclesiastical authorities, who fabricated documents, backdated events, and created false historical records to extend their own perceived reign and establish a more impressive timeline of Christian dominance. What makes this theory psychologically compelling is that it exploits genuine gaps in our historical record, real instances where documentation becomes sparse or unreliable, and the undeniable truth that much medieval history relies on fragmented sources that were themselves written long after the events they describe. The human mind seeks patterns and coherence in chaotic information, and the phantom time hypothesis offers a seductive narrative that transforms confusing historical ambiguities into a singular, dramatic conspiracy, rather than accepting the uncomfortable reality of simply not knowing. Furthermore, the theory preys on our awareness that powerful institutions have indeed falsified records throughout history, which lends it a surface plausibility despite lacking actual evidence or mechanism for how such a conspiracy could succeed across all of Europe simultaneously. The hypothesis persists in certain circles despite being thoroughly rejected by academic historians, archaeologists, and chronologists who have demonstrated consistency in dating through multiple independent methods, including radiocarbon analysis, dendrochronology, geological stratification, and cross-referenced primary sources from countless cultures that had no reason to coordinate fictional timelines. Yet the appeal endures because it represents a deeper human anxiety about the reliability of our collective memory, the terrifying possibility that the foundations of our historical understanding might be fundamentally compromised, and our perpetual susceptibility to grand narratives that transform uncertainty into false certainty. In this way, the phantom time hypothesis functions as a mirror reflecting our modern crisis of institutional trust, where each new revelation of historical revisionism or institutional deception seems to validate the possibility that even our most fundamental certainties could be elaborate fictions waiting to unravel. Yet paradoxically, this very distrust in institutions becomes the theory's primary fuel. Each academic dismissal of the hypothesis is reinterpreted as evidence of a cover-up, transforming the skepticism that should undermine the theory into proof of its validity, creating a self-sealing logical trap where no amount of contrary evidence can penetrate. Imagine for a moment that everything that has ever happened, is happening now, and will ever happen exists simultaneously in a four-dimensional structure called spacetime, laid out like a complete block of marble where past, present, and future are equally real and equally fixed. This is not philosophy or metaphor, but rather the serious conclusion of Einstein's theory of relativity, which fundamentally changed how physicists understand the nature of time itself. According to this model, the universe is not a flowing river, where the present moment carries us forward into an unknown future, while the past fades into memory and irrelevance. Instead, the entire timeline of existence, from the Big Bang to the final moments of the cosmos, exists in its totality right now, eternal and unchanging, a four-dimensional block where your birth, your death, every conversation you will ever have, and every moment of joy or suffering already exists as a permanent fixture of reality. The mechanism behind this counterintuitive idea emerges directly from relativity's revelation that time is not universal but relative, that simultaneity depends on the observer's frame of reference, and that the past and future do not occupy fundamentally different ontological categories than the present. If observers in different reference frames can legitimately disagree about which events are happening now, then the concept of a special moving present moment loses its physical meaning, leaving us with a static, unchanging structure where all moments coexist without hierarchy. What makes this particularly disorienting is that we have normalized an entirely different experience in consciousness, where we feel a constant arrow of time, where decisions seem genuinely open until made, and where the future remains genuinely undetermined and unknown. We live with the persistent sensation that only the present is real, that we are actively creating the future through our choices, and that the past, while fixed, is at least absent and gone. Yet the mathematics and observations that have guided scientific progress for over a century suggest this entire framework of experience is illusory, that our felt sense of time's flow is perhaps the grandest delusion consciousness can conjure, and that in the deepest layers of physical reality, nothing is truly created, nothing genuinely passes away, and everything that ever was or will be simply is, frozen forever in the eternal block of space-time. If this is true, then the distinction between memory and anticipation collapses into mere perspective. What we call remembering the past is simply observing an earlier region of the block, while imagining the future is observing a later region, both equally present, equally real, and equally beyond our control or creation. And yet, if every moment of your life, your first kiss, your greatest triumph, your final breath, already exists in equal permanence within this block, then perhaps the question of whether you have free will becomes not a scientific problem to solve but a conceptual confusion to dissolve. For in a universe where all moments coexist eternally, the very notion of choosing between alternatives that don't yet exist may be fundamentally incoherent. When we examine the fundamental laws of physics at the microscopic level, we encounter a peculiar and unsettling asymmetry that appears nowhere in the equations themselves. The laws governing individual particles and their interactions are essentially time-reversible, meaning that if you filmed a collision between atoms and played it backwards, the reversed version would be equally valid, according to the mathematics of quantum mechanics and classical mechanics alike. Yet in our everyday experience, time flows in one direction only, from past to future, with an irreversible arrow that creates the distinction between cause and effect, memory and anticipation, and birth and death. This apparent contradiction between the time-reversible nature of microscopic physics and the time-directed nature of macroscopic experience remains one of the deepest mysteries in science, a gap that physicists have attempted to bridge through concepts like entropy and the second law of thermodynamics. The explanation typically invokes the notion that systems naturally progress toward greater disorder and randomness, yet this explanation itself becomes circular when examined closely, because entropy itself is only directional when we already assume the arrow of time. The psychological mechanism that allows us to live comfortably with this unresolved contradiction relies on a kind of compartmentalization, where we accept the time-reversible laws of physics in our scientific frameworks, while simultaneously organizing our entire conscious experience around an irreversible temporal progression that those same laws cannot fully explain. We remember the past but not the future, we age in one direction, our decisions change the future but not the past, and yet the deepest level of physical reality gives no mathematical reason why this should be so. Despite centuries of investigation and increasingly sophisticated theoretical frameworks, this fundamental asymmetry persists in the gap between our equations and our experience, and we continue functioning in daily life without resolution to this paradox, having essentially normalized the idea that physics cannot explain one of the most basic features of reality as we perceive it. Perhaps the most humbling aspect of this situation is that the arrow of time may not be a feature of the universe itself, but rather an artifact of our position within it, a perspective-dependent phenomenon that emerges only when consciousness attempts to organize the infinite complexity of a fundamentally timeless reality into a coherent narrative of cause and effect. If this interpretation holds truth, then our sense of time's direction may be less like a discovery about nature and more like a story we tell ourselves, one so deeply woven into consciousness that distinguishing the narrator from the narrative becomes nearly impossible, leaving us forever uncertain whether we are reading time's arrow or writing it. And yet we persist in the attempt to read it, constructing ever more elaborate instruments to measure time's flow, running experiments that presume the very directionality we seek to understand, trapped in a logical loop where our tools for investigation are themselves products of the arrow we hope to explain. There exists a profound paradox at the heart of human knowledge that few people genuinely pause to contemplate. Mathematics, a system we invented entirely within our own minds, describes the physical universe with an accuracy so uncanny that it borders on the supernatural. We created abstract symbols and rules, numbers, equations, geometric proofs, as mental tools to help us organize our thoughts and solve practical problems, yet these invented concepts somehow map onto reality with stunning precision. Bridges built using mathematical principles stand for centuries. Spacecraft launched using calculated trajectories reach distant planets millions of miles away. Medical imaging devices powered by mathematical algorithms detect cancers invisible to the naked eye. The predictions made by mathematical models align with observations so consistently that it seems impossible they could merely be coincidence. When physicists write an equation on a blackboard, they can predict the behavior of particles that won't be experimentally confirmed for decades, and they are proven right with astonishing regularity. When engineers calculate the stress distribution across an airplane wing using differential equations, that plane carries hundreds of people safely through the sky. This is not failure occasionally followed by success. This is systematic, reliable, almost eerie accuracy emerging from a system that originated entirely as human invention. The mechanism behind this apparent miracle involves recognizing that mathematics may not actually be invented, but rather discovered. Perhaps the patterns we perceive through mathematical language exist independently in the structure of reality itself, and mathematics is simply our tool for translating those patterns into a form our minds can comprehend and manipulate. The universe operates according to underlying laws and symmetries, and mathematics appears to be the language in which these laws are written. When we discover a mathematical relationship, we may be uncovering something that was always there, waiting to be found. Our brains, shaped by evolution to survive within this universe, may be naturally tuned to recognize the abstract patterns that reflect its fundamental structure, making our invented symbols feel less invented and more like a discovery of something pre-existing. What makes this phenomenon so unsettling is that we have thoroughly normalized it without adequately grappling with its implications. We treat the unreasonable effectiveness of mathematics as simple fact, expected and unworthy of wonder, yet we have never truly explained why a system of abstract symbols created in human minds should describe physical reality at all. The mystery persists in plain sight, hiding beneath layers of habituation and acceptance, reminding us that the relationship between consciousness and reality may harbor depths far stranger than our everyday experience suggests. Perhaps this is why mathematicians so often report that their discoveries feel less like creation and more like archaeology, as if they are carefully brushing away dust to reveal truths that have always existed in some abstract realm, waiting patiently for human minds sufficiently evolved to perceive them.